Hello there, and welcome to Science for Sleep, where curiosity settles gently beside you and the universe becomes something you can explore without pressure or hurry. Tonight, we're drifting toward a place you've never seen, but that has shaped every moment of your existence from the day you were born. It sits far away, hidden behind dust clouds and starlight, wrapped in silence at the very center of our galaxy. It has no surface, no colour, no light, yet somehow it holds everything around us in place. It guides the motion of our sun, it shapes the paths of billions of stars, it anchors the great spiral pattern of the Milky Way. And even though you've never felt it directly, you've lived your entire life under its influence. Tonight we're heading to Sagittarius A, the supermassive black hole that acts as the quiet gravitational heart of our home galaxy. Before we wander too far into that darkness, I'd love to know where you're listening from tonight. Are you somewhere quiet? Maybe tucked in bed? Maybe settling down after a long day? And what time is it for you right now in your corner of the world? It's a strange thought that we're talking about the centre of the Milky Way while each of us sits somewhere out on one of its spiral arms, separated by tens of thousands of light years. Yet here we are, meeting in this one shared moment. If you find this journey comforting or interesting or simply a gentle way to drift toward rest, I'd be grateful if you'd like the video or subscribe. It helps more wandering minds find their way here. Now let's settle in a little deeper. There's something almost soothing about imagining distances so big that ordinary problems shrink away. Something reassuring about thinking of a structure so enormous and so constant that it feels like an anchor, even though we cannot see it. Sagittarius A sits about 26,000 light years away from us. If you were somehow able to travel toward it at the speed of a light, it would take you longer than human civilization has existed just to reach its location, and even if you arrived, you wouldn't see anything at first. There's no glowing sign, no swirling drain in space, no dramatic pulling effect from afar. What you'd see instead is a crowded neighbourhood of stars, dense in a way unlike anywhere else in the galaxy. The region near the centre is packed with gas, dust and clusters of stars orbiting much faster than stars do out where we are. Their speeds would be the first hint that something massive is hiding in the shadows. It might be surprising to learn that the entire idea of a black hole isn't something that appeared with modern science fiction. A few centuries ago, some physicists started wondering what would happen if an object was so compact that even light couldn't escape its pull. They didn't have the mathematics to prove such an object could exist, and the idea quietly drifted into the background for years. It wasn't until Einstein's general theory of relativity that the concept gained real structure. Relativity predicted that if enough mass were concentrated into a small enough region, it would create a gravitational effect so intense that the fabric of space itself would curve inward, preventing anything, even light, from climbing back out. Even then, many scientists were uneasy with the idea. It felt too extreme, too unphysical. But nature doesn't mind making things that challenge us. And at the centre of the Milky Way, nature created something astonishingly massive, roughly 4 million times the mass of our Sun, all compressed into a region smaller than our planetary orbit around that Sun. Imagine the entire solar system squeezed into a space not much larger than the distance between the Earth and the Sun, and then imagine that instead of a bright star filling that space, there is something completely dark. The strange part is this. Sagittarius A doesn't pull everything inward in some cosmic gulping motion. Space doesn't behave like that. Instead, everything nearby simply follows the curved paths that gravity shapes. Much like planets orbit the Sun because of its mass, stars orbit Sagittarius A because its gravity defines the shape of their environment. The entire galaxy rotates around its centre, not because the black hole acts like a cosmic drain, but because its mass adds to the gravitational balance that holds the Milky Way together. Without it, the dance of stars would be different. The spiral arms would be shaped differently. our sun's orbital path would shift. The overall structure of the galaxy would not be the same. You wouldn't be here in the exact way you are now. At a deep level, your entire life has been shaped by the gravitational influence of this unseen object. When astronomers first looked toward the centre of the Milky Way, they couldn't see much. Dust clouds blocked visible light. For years, the centre was just a region of radio emissions and infrared glow. Telescopes improved slowly, and the picture sharpened, but there was still nothing obvious that looked like a black hole. The breakthrough came from watching the motion of the stars near the core. Several research teams began tracking specific stars over many years. They followed their paths, noted their speeds, charted their orbits as they curved tightly around a point that was completely dark. These stars weren't drifting lazily. They were whipping around at thousands of kilometers per second. Some moved so quickly that it was clear only a truly massive compact object could possibly explain their behavior. Over time, the orbits traced by those stars formed a kind of signature. All of them curved around the same invisible location. All of them moved too quickly for anything other than a supermassive black hole to be there. It was like watching the hands of a clock whose centre remained invisible, but whose presence you could detect from the motion around it. Thinking about this can feel strangely grounding. The idea that something so enormous and so powerful can be completely silent teaches us something about the universe. Not everything that shapes us announces itself. Not everything important is visible from the outside. Sometimes the strongest forces in your life are the ones that don't glow or scream or draw attention. They simply pull quietly, constantly, steadily. That's part of what makes Sagittarius A so fascinating. Even though it's millions of times heavier than the Sun, it's not some violent force pulling the galaxy inward. It's not a threat to us. We're too far away, moving in our long, steady orbit on one of the spiral arms. It exerts its pull across the entire galactic structure in the same way a central weight pulls on the spokes of a wheel. Gravity governs the motion of stars, and in doing so, it also creates the environment necessary for planets to form, for suns to shine, for life to arise. It's remarkable to think that something so distant and so invisible plays such a fundamental role in our existence. Without it, the Milky Way might not be a spiral. The solar system might not have formed where and how it did. Earth might not have been here at all. There's also something strangely calm about thinking of black holes realistically rather than through dramatic stories. They don't roam the galaxy swallowing stars at random. They don't tear apart everything in their path. They sit where they are, affecting the space around them much like any massive object does. If our Sun were replaced by a black hole of the same mass, Earth would continue orbiting it in almost the same way, though of course we would lose its light and warmth. Gravity doesn't behave differently just because something is a black hole. The dramatic effects happen only near the event horizon, the point where escape becomes impossible. Far away, the gravitational pull feels normal. The centre of the galaxy is far more crowded than the region where we live, and the material around Sagittarius A can sometimes create bursts or flares when gas gets heated as it approaches the event horizon. But these events are brief and rare. For the most part, the black hole rests quietly. It isn't currently feeding heavily on nearby stars or gas clouds. It's more like a sleeping giant, influencing everything by its presence rather than its activity. When scientists finally managed to image the area around Sagittarius A using a network of telescopes called the Event Horizon Telescope, it wasn't the black hole itself that appeared, but the glow of heated material surrounding it. Even still, the result revealed the shadow of the black hole, the absence of light against the bright background. That dark central shape was the first direct visual evidence that the object we had inferred for decades truly existed. Standing back from all the details, it helps to imagine the Milky Way as a vast rotating disk of stars. The Sun takes about 230 million years to complete one full orbit around the centre. That means the solar system has only completed a handful of such orbits since Earth formed. Each time life arose, changed, or vanished, the Sun was in a slightly different place in the galaxy. yet the center remained the same, a stable gravitational anchor. Sagittarius A has been there throughout every chapter of the galaxy's history, shaping its structure long before any planet cooled enough for oceans to form. And here we are, sitting on a small planet in a quiet part of a spiral arm, thinking about an invisible object far away that has been influencing our motion since long before humans existed. There's something comforting in that sense of scale. No matter what happened in your day, the galaxy continued turning. The sun continued along its orbit. Sagittarius A continued its steady pull. You are part of a structure so large and so stable that it can hold both chaos and calm without faltering. The center of our galaxy is one of the busiest regions anywhere in the Milky Way, yet the object we're focusing on now remains completely invisible. You could stare straight at it with your eyes, with an ordinary telescope, or even with advanced instruments that capture visible light, and you wouldn't recognize anything unusual. It sits behind thick lanes of dust and gas that stretch across tens of thousands of light years, blocking and scattering the kind of light we naturally see. If you didn't know better, you might think the region was simply crowded, dense and chaotic, but nothing more, and yet hidden inside that dark patch is one of the most massive things our galaxy has ever produced. It isn't glowing. It isn't radiating like a star. It isn't shining like a nebula. It isn't even moving in any way we can visually track. It is simply there, shaping everything around it through gravity and nothing else. Thinking about something so enormous that remains completely unseen can feel a little strange at first. Most of the big things we interact with in everyday life are obvious. Mountains stand tall, oceans stretch to the horizon, storm clouds gather visibly. But the universe often hides its most powerful objects behind layers that our senses were never built to penetrate. Sagittarius A is a perfect example of this. 4 million times the mass of the Sun, compressed into a region small enough that light itself cannot escape. If the Sun were somehow turned into a black hole, it would be only a few kilometers across. A supermassive black hole like the one at our galactic center is larger, but still tiny compared to the space around it. Nothing about its size would reveal its mass if you could somehow stand at a safe distance and look into the dark. The gravitational influence is the only indication that something extraordinary is there. This hidden nature is part of what makes it feel almost gentle from far away. We tend to imagine black holes as dangerous, violent objects, but Sagittarius A is not tearing apart stars on a regular basis. It is not swallowing huge streams of gas every day. Most of the time, it behaves like a quiet, heavy object anchored in place. Its gravity shapes the orbits of nearby stars, but it isn't actively consuming them. The picture many people carry from dramatic stories or movies, swirling disks, high-speed jets, loud eruptions, doesn't match the reality of this particular black hole. The environment around it can produce flares when small pockets of gas fall inward, but those events are occasional and quickly fade. Otherwise, it remains calm, behaving like a silent weight deep in the dark. Although Sagittarius A doesn't reveal itself through visible light, the region around it emits energy at wavelengths our eyes can't detect. Radio telescopes, infrared instruments, and X-ray observatories have been essential in uncovering its presence. Decades ago, astronomers detected strong radio signals coming from the center of the Milky Way. These signals didn't come from a star or a typical source. They were compact and persistent. As instruments improved, scientists traced them to a region so small and so dense that ordinary explanations weren't enough. The radio source was eventually labeled Sagittarius A, with the asterisk indicating a very particular point-like object. For years, that label was attached to data, graphs and survey maps, long before it became widely known that it represented a supermassive black hole. This kind of scientific detective work is part of what makes the discovery so intriguing. No one could see Sagittarius A directly. Instead, astronomers watched how stars behaved near the center. They plotted their positions, measured their speeds, and looked for patterns. Over time, small movements became clearer. A star slightly shifted from where it had been a year earlier. Another followed a curve that made little sense without a powerful source of gravity nearby. One star in particular, often called S2 in research papers, completed a full orbit around the invisible object in just over 16 years. To complete such a fast, tight orbit, the central mass had to be enormous and extremely compact. Nothing known except a black hole could fit the requirements. When you think about it, this method of discovery is similar to noticing something heavy sitting on a table by watching how the table bends. You might not see the object itself, but you can infer its presence from how the environment responds. The orbits of stars acted like that bending surface, revealing the heavy, unseen center. This is how we came to understand that the silent region wasn't empty. It was one of the most massive objects we've ever detected. It helps to picture what the area near Sagittarius A would look like if you could somehow stand in a protected location nearby. You wouldn't be close enough to the event horizon to experience anything extreme. Instead, you'd see a star field far more crowded than the one above Earth. Stars of many kinds would be scattered across the sky, bright enough to cast faint shadows. Their speeds would be something you could actually measure over time without advanced equipment. Some would appear to drift across the sky noticeably from one year to the next. That's how fast they orbit the center. The region would feel alive with movement, but the centerpiece of all that motion would remain completely hidden. It's unusual to think of something so powerful being so quiet. In our daily lives, strength is often accompanied by noise or movement. Heavy machinery hums, engines roar, waves crash. Even strong wind makes sound as it passes through trees and buildings. But gravity doesn't make sound. Space is mostly empty. There is no air to carry vibrations. A black hole does not announce itself with any kind of noise. It merely curves space in a way that everything around it must follow. Silence is part of its nature. One interesting aspect of this stillness is how stable Sagittarius A has remained over millions of years. Supermassive black holes can go through very active periods in the early lives of galaxies. During those times, they pull in large amounts of gas and dust, causing intense heating, bright jets, and energetic outflows that can shape entire galaxies. But that phase tends to settle down as material near the center becomes sparse. Today, Sagittarius A is in a quiet state. It isn't erupting, it isn't feeding heavily, it isn't shining like the core of a quasar. It simply sits, influencing the structure of the galaxy without drawing much attention. If you could observe it from a safe vantage point for long enough, you might occasionally see a small flare when hot gas gets close enough to be heated, before disappearing into the horizon. These flares are brief and faint compared to the activity seen in more energetic black holes in distant galaxies. They offer hints about how matter behaves under extreme gravity, but they do not disturb the overall calm environment around the center. The black hole does not change dramatically from day to day or year to year. Its presence is constant and steady. Some people imagine that stars are constantly falling into Sagittarius A, but that isn't happening. The orbits of nearby stars are stable. They've been moving around the center for millions of years and will continue doing so for millions more. Black holes do not randomly pull in distant objects. Anything that falls in must lose energy, or move close enough for gravity to take over. Most stars maintain their distance and simply continue along the orbit shaped by the central mass. The balance between gravity and motion keeps the region surprisingly orderly, despite how dense it is. There's something comforting about this idea of order. Even in a place where gravity is incredibly strong, the overall structure is predictable. Stars follow paths determined by the mass at the center. Gas clouds move under the same influence. The black hole doesn't disrupt this pattern unless material drifts too close. From a distance, it behaves like a quiet anchor. Its influence defines the motion of the entire core, but it does so without noise or visible activity. When the Event Horizon Telescope produced an image of the region around Sagittarius A, it confirmed what decades of indirect evidence had already shown. The dark central region matched the expected shape of a black hole's shadow. The surrounding glow came from gas heated as it circled near the event horizon. Even though the image was blurry and difficult to interpret without understanding the technique behind it, the details aligned with the predicted structure. Once again, the object revealed itself not by shining but by the absence of light. The shape of that absence matched the mathematics of general relativity. It was a quiet but powerful confirmation that the invisible mass was exactly what astronomers believed. This silent nature also highlights something important about how we study the universe. Many of the most profound discoveries are made not through dramatic sights, but through careful measurements. We learn about the structure of galaxies by tracking motion. We learn about planets around distant stars by observing tiny dips in brightness. We discover black holes by examining how stars behave near them. A great deal of our understanding comes from looking for patterns that repeat over time. Sagittarius A is one of the most studied objects in the sky, not because it flashes or glows, but because the clues it leaves behind are remarkably consistent. It's worth thinking about how different our view of the galaxy would be if the centre were not blocked by dust. If you could see straight in with your eyes, the core would be the brightest part of the sky every night. The stars there would appear concentrated into a glowing region that dominated the view, but the dust lanes get in the way, scattering and absorbing visible light. As a result, the centre looks like a faint patch to us. We need specialised instruments to see what lies beneath. This limitation isn't a flaw, it's part of how the universe works. We build tools that extend our senses, and in doing so, we discover things that were always there, just beyond our natural reach. Over time, as you think more about Sagittarius A, it becomes less like a frightening concept and more like a stable presence. It's difficult to fear something that simply exists, quietly shaping the galaxy without disrupting our daily lives. The black hole isn't an enemy or a threat. It's part of the structure that allows the Milky Way to exist the way it does. Without a massive object at the centre, the galaxy's rotation would not be balanced in the same way. Spiral arms might not form the same patterns. The distribution of stars would change. Everything about our environment in space would look different. Seeing it this way turns the black hole into something more like a silent foundation than a destructive force. It's an object whose existence helps create the conditions for everything else. There's no intention behind this, of course. It's simply a result of gravity acting on vast amounts of matter. But understanding that relationship helps remove the sense of mystery or danger often attached to black holes. Instead, they become interesting examples of how space responds to mass on extreme scales. When you picture the Milky Way, it's easy to imagine a grand spiral stretching across space, glowing softly with billions of stars arranged in curved arms. It seems almost delicate from a distance, like something that could drift apart if nudged the wrong way. But galaxies aren't loose collections of stars. They're bound structures held together by gravity, shaped by influences that stretch across vast distances. In the case of the Milky Way, the heavy object at the centre plays a role in this structure, setting the balance for motion closer to the core and contributing to the galaxy's overall stability. Even though the galaxy contains far more mass in stars, gas, dust, and dark matter than in the central black hole, the presence of Sagittarius A helps define the behaviour of everything near the centre, and indirectly influences the larger arrangement of stars, including the spiral pattern we see when looking at images of our home from a simulated outside view. Thinking about this requires stepping back far enough to see the Milky Way not as something artistic or symbolic, but as a physical object where motion follows rules shaped by mass and distance. Every star in the galaxy, including our Sun, moves in a wide orbit around the centre. The Sun is roughly 26,000 light-years from Sagittarius A, far enough that its orbit takes around 230 million years to complete just once. That means the entire history of humanity occupies only the tiniest fraction of a single orbit. For nearly all of human history, Earth has been in almost exactly the same tiny segment of its path. Even the entire age of the dinosaurs represents only a handful of loops around the galactic centre. The fact that our star continues in a predictable orbit tells you something important. The mass distribution of the Milky Way is stable enough that stars remain on consistent paths over enormous time spans. Sagittarius A, occupying the very centre, contributes to this stability, not by dominating the entire galaxy, but by anchoring the motion near the core and influencing the gravitational shape of the region. Without a sufficiently massive object in the centre, stars there would not orbit in the same tight, fast loops. The lack of a central mass would alter how the inner region holds together, and small changes near the core can have effects that ripple outward. It's helpful to picture the galaxy as a spinning disk. If the centre were too light, the spin would be different. If it were too heavy, the spin would shift the other way. Sagittarius A represents the mass at the centre that allows the inner galaxy to rotate in a stable manner. It isn't holding the entire galaxy together by itself, but it contributes to the deeper gravitational framework that allows the Milky Way to have the shape we see today. Another way to think about this is by imagining a whirlpool, not in the dramatic sense used in films, but in the gentler physical sense where water moves in a circular pattern around a central point. The central point doesn't need to be pulling everything downward. It simply has to define the motion of the water around it. In the Milky Way, the central black hole is that defining point. It shapes the orbits of the innermost stars and adds to the overall gravitational potential that holds the galaxy together. Around it, the density of stars increases dramatically compared to the spiral arms where we live. The inner region is crowded, hot and active, and those conditions require a strong central mass to maintain their structure. The interesting part is that even though Sagittarius A is enormous, it isn't the majority of the galaxy's weight. The Milky Way contains hundreds of billions of stars, plus vast clouds of gas and an invisible halo of dark matter that makes up most of the galaxy's mass. In comparison, the black hole is only a small fraction of the total, yet it still plays a meaningful role. The same way a heavy weight placed at the centre of a spinning wheel helps stabilise its motion, a supermassive black hole at the centre of a galaxy helps define the structure of the inner region. Without that anchor, the distribution of stars near the core would be different. For stars located very close to Sagittarius A, its influence is unmistakable. Their orbits are fast and narrow. Those stars move in ways that can only be explained by the presence of an object millions of times heavier than the Sun. But even stars far away feel the effect, not in a dramatic way, but as part of the overall gravitational field that the black hole contributes to. It is one part of the combined forces that shape the galaxy's rotation. One of the most surprising discoveries in astronomy is that many galaxies, maybe even most, contain supermassive black holes at their centres. The more we observe galaxies across the universe, the more clear this pattern becomes. There seems to be a relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. Large galaxies tend to have heavier black holes, smaller galaxies tend to have lighter ones. The reason for this relationship is not fully understood, but it suggests that black holes and galaxies grow together, influencing each other over billions of years. In the early stages of galactic formation, material collapses under gravity to form stars, clusters, and eventually larger structures. At the same time, regions of dense matter may collapse into black holes, and these black holes can grow by absorbing gas or merging with others. As they grow, they affect how gas flows near the centre of the galaxy. Those flows can control where new stars form and how the inner regions behave. Over time, galaxies settle into the shapes we see today, and supermassive black holes remain at their centres as relics of that long process, still influencing their environment even when they stop actively feeding. Sagittarius A is an example of a black hole in a quiet phase. It no longer pulls in enough material to shine brightly as an active galactic nucleus. But in the past, it may have been far more energetic. evidence suggests that it emitted powerful outflows at some point millions of years ago. Those outflows are faint today, seen only as subtle structures in the surrounding gas. Whatever activity happened back then has long since faded. Now the centre of the Milky Way is relatively calm, allowing stars to orbit steadily without the intense radiation or jets that active black holes produce. Even in this quiet state, Sagittarius A continues to shape the inner galaxy. Think of it as a stable anchor that has survived across cosmic time. Long before Earth existed, before the Sun formed, before the spiral arms took their present shape, the central black hole was already influencing the motion of stars near the core. As new generations of stars formed and old ones died, the gravitational environment remained consistent. Hundreds of millions of years pass, and the black hole remains, guiding the motion of everything around it with a steady pull that does not change quickly. Although gravity is the primary force at work here, it doesn't only control large structures. Even the gas clouds near the centre feel its influence. These clouds are thick, warm, and constantly shifting. When they pass close enough to the central black hole, they can be stretched, compressed, or heated by the gravitational forces. This changes how they move and how stars form within them. Over long periods, this constant shaping influences the development of the entire region. The black hole's gravity isn't a sudden or violent presence. It's a continual, steady factor that gradually affects the shape of everything nearby. This kind of long-term influence can feel almost strange to grasp. Humans experience time in hours, days, years. A long project might take months. A life contains decades. But galaxies evolve across millions and billions of years. Their motion is slow when viewed from our perspective, even though stars move rapidly across enormous distances. When you imagine Sagittarius A holding its position at the centre decade after decade, century after century, and then stretch that further into millions of years, the scale of stability becomes clearer. The galaxy's rotation is slow enough that the inner structure has time to settle into a pattern shaped by mass distribution, and the black hole contributes to that distribution. Understanding this stability also helps reduce the sense of danger often associated with black holes. Many people imagine black holes as entities that pull in everything around them, but that's not how gravity works. A black hole influences motion just like any other massive object. If the Sun became a black hole of equal mass, Earth would continue orbiting more or less exactly as it does now. The only difference would be the loss of sunlight. Gravity would not suddenly increase. The same principle applies to Sagittarius A. Its influence is strong near the centre, but for stars in distant regions like ours, it acts as part of the combined mass of the galaxy. It isn't waiting to consume anything. Objects fall in only if they lose enough energy or pass extremely close. Most stars keep their distance for millions of years. One especially interesting aspect of the Milky Way structure is how the black hole interacts with other components, such as the bulge of stars surrounding the core and the dark matter halo that extends far beyond the visible disk. The bulge is a densely packed spherical region of stars. Its mass also contributes to the gravitational shape of the inner galaxy. The dark matter halo too plays a major role in supporting the galaxy's shape and motion. Sagittarius A is not the dominant mass among these structures, but it serves as a central point that defines the inner, most gravitational well. Other components shape the outer regions, while the black hole shapes the behaviour closest to the centre. When you combine all of these elements together, stars, gas, dark matter, and the black hole, you get a galaxy that rotates in a stable pattern. Each part influences the others. Remove one, and the structure would change. The black hole is one important part of that arrangement. It maintains the inner motion and supports the long-term stability that allows the Milky Way to remain a spiral galaxy rather than something more chaotic. It's reassuring in a way to think about the galaxy as a system that maintains balance over such long periods. Life on Earth can feel unpredictable. Seasons change quickly, weather shifts, human events move fast. But overhead, at scales too large for immediate awareness, the galaxy continues its rotation at a pace that does not rush or hesitate. Sagittarius A remains at the centre, providing a constant gravitational reference for everything around it. The stars closest to the centre of the Milky Way behave in ways unlike anything we see in the quieter regions where our own solar system lives. Out here, stars move slowly enough that you would never notice a change in their positions during a human lifetime without careful measurement. Their motion is steady and predictable, but it feels almost still to the human eye. Near Sagittarius A, the story is very different. Stars there rush along paths so curved and so fast that astronomers can track their movement across the sky year after year, watching them trace loops around something that remains completely invisible. The first time scientists began measuring the orbits near the centre, many expected to find something unusual, but not necessarily something as extreme as a supermassive black hole. Observatories with infrared capability started looking deeper into the dusty region that blocks visible light. What they found was a cluster of stars packed together more tightly than almost anywhere else in our galaxy. These stars weren't drifting lazily. They were racing through space at speeds that would seem unbelievable at a human scale. Some of them moved at thousands of kilometers per second, completing full loops in periods that don't match anything we see in the outer parts of the galaxy. Tracking these stars took patience, because their movements needed to be measured over long periods. Astronomers marked their positions year after year, then plotted their trajectories, looking for patterns that might reveal what lay at the centre. Imagine watching the hands of a clock, except the clock face is made of dusty gas clouds, and the hands are stars moving in tight circles around a point of complete darkness. Over time, those paths became clear. The stars weren't following random curves. They traced well-defined orbits that all centered on a single location. The size of the region they orbited was extremely small compared to the speeds involved, which meant that whatever sat at the center had to be extraordinarily massive. One star in particular, often referred to as S2 in scientific papers, became a turning point in understanding the center of the galaxy. This star completes its orbit in just over 16 years. When you consider that our Sun takes more than 200 million years to circle the galaxy once, a 16-year orbit is extraordinary. That orbit allowed astronomers to calculate the mass of the object at the center with remarkable accuracy. By measuring the speed and curvature of S2's path, scientists could determine that the central mass is around 4 million times that of the Sun. Nothing else besides a supermassive black hole could account for such a dense concentration of mass in such a small region. If you could observe S2 up close, it would be a dramatic sight. The star swings incredibly close to the black hole on the tightest part of its orbit. At its closest point, it travels at speeds that stretch the limits of what stars can handle. Even at that distance, S2 is safe. It moves too quickly to fall inward, held on its path by the balance between its speed and the gravitational pull of the black hole. When it rounds the closest part of its orbit, it slingshots away, moving back into the wider part of its loop. This pattern repeats over and over, forming a long-term, stable orbit that reveals details about the central mass. Every star near Sagittarius A responds to the force of the black hole, but each does so in a slightly different way. Some stars move in long ovals, others move in tighter, almost circular paths. A few close enough to be strongly influenced move in dramatic curves, completing loops in only a few decades or less. These orbits are not aligned neatly like planets in the solar system. They move in various angles and orientations, creating a complex three-dimensional distribution rather than a flat, organized disk. This variety gives astronomers even more information, because the shape of each orbit helps refine the estimate of the black hole's mass, the distribution of matter around it, and the gravitational environment. One of the reasons these stars are so important is that the center of the Milky Way is an ideal environment for measuring the effects predicted by general relativity. Relativity describes how gravity affects space and time. In most places, the differences between Newtonian gravity and relativistic gravity are too small to notice. But near a supermassive black hole, the differences become measurable. The way stars speed up, slow down, or shift slightly in their orbits can reveal how space curves near the event horizon. When S2 made its closest approach in 2018, astronomers observed a phenomenon known as gravitational redshift. This effect occurs when light loses energy while climbing out of a deep gravitational field. The light from S2's surface stretched slightly toward longer wavelengths as it escaped the black hole's strong pull. This confirmed a key prediction of general relativity. The star acted like a test particle moving through curved space, and its behavior matched exactly what Einstein's equations forecasted. Stars in the central region also experience something called orbital precession. It means that the orientation of their orbit changes slightly each time they complete a loop. Instead of tracing the same exact path, the orbit shifts forward, creating a rosette-like pattern over time. This behavior was first noticed in the orbit of Mercury around the Sun. But near Sagittarius A, the effect is far more pronounced because the gravitational field is much stronger. Watching the orbits change over many years helps scientists understand the structure of space near the black hole and test theories of gravity under extreme conditions. The stars that orbit close to Sagittarius A are often referred to as S-stars in scientific literature. Many of them are surprisingly young. Their youth raises interesting questions because the conditions near the centre aren't ideal for forming stars. The region is turbulent, crowded, and filled with intense gravitational forces. Some theories suggest that these stars might have formed farther out and then migrated inward. Others propose that star formation could occur in bursts due to the compression of gas clouds near the black hole. Whatever the explanation, their presence provides valuable insight into how matter behaves under extreme gravitational influence. There's something compelling about imagining these stars from a perspective much closer than anything we can actually reach. If you could somehow place yourself in a safe position in the region near the centre, the night sky would look completely different from what you're used to. Stars would fill the sky in every direction, and some would move noticeably over weeks or months. If you happened to watch one of the S-stars during its closest approach, you would see it accelerate across the sky, then gradually slow as it moved into the outer part of its orbit. The sense of motion would be much more immediate than the slow drift of constellations we see from Earth. Despite the extreme speeds and tight orbits, these stars are stable. They have been moving around the black hole for long periods and will continue to do so. Their paths are governed by predictable gravitational laws. Even though the black hole's influence is intense, the stars aren't spiraling inward. They maintain their orbits much like planets maintain their orbits around the Sun. The difference is simply in scale and speed. The gravitational field near Sagittarius A is far more powerful than what we experience in our solar system, but the fundamental principles are the same. The motion of these stars is one of the strongest pieces of evidence that supermassive black holes exist. Before these observations, many scientists considered black holes theoretical. They were predicted by mathematics and supported by indirect clues, but no one had observed anything that conclusively matched the expected behavior. The orbits near the centre of the Milky Way provided the clearest, most direct proof. Watching stars curve sharply around an unseen object with such extreme speed left little room for alternative explanations. A cluster of smaller objects couldn't create a gravitational pull that's strong without collapsing into a black hole. A dense mass of exotic material would also be unstable. The simplest explanation, the one supported by the data, was that a supermassive black hole sits at the centre of the galaxy. Seeing how gravity shapes these orbits also helps ground the idea that black holes are not strange anomalies in the universe. They are natural consequences of matter collapsing under its own weight. They follow the same rules that govern the motion of planets, moons, and stars everywhere else. The difference is only in the extreme nature of the environment. The closer you get to the event horizon, the more intense the gravitational effects become. But farther away, motion follows familiar patterns. There's something reassuring about that. Even in one of the most extreme environments in the galaxy, order persists. Stars move in stable, predictable paths. Their motion reveals the presence of something unseen, but it doesn't show chaos. It shows structure. The black hole does not distort their behavior in erratic ways. It simply curves the space they move through, and they follow the paths shaped by that curvature. Over time, studying these orbits has also allowed astronomers to refine the mass estimate of Sagittarius A. Each additional orbit observed adds more data. As more stars attract, the overall picture becomes clearer. The black hole's mass is now known with remarkable precision. Its position is known within extremely small limits, and the shape of the space around it is mapped more accurately with each passing year. The stars act as markers, tracing out the gravitational landscape in a way that gives us insight into something we cannot see directly. Even the absence of light from the black hole contributes to the picture. When stars pass close to it, their light is not blocked by an object. Instead, the region remains dark. There is no shining surface, no reflective boundary. This darkness is part of what confirms the nature of Sagittarius A. If it was something other than a black hole, such as a dense cluster of objects, it would emit light, heat, or radiation from its surface. But the region remains silent and invisible, consistent with what we expect from a black hole, where the event horizon marks the point of no return. Light cannot escape from inside, so the center stays dark no matter how much material surrounds it. Thinking about these stars also adds perspective to our own position in the galaxy. Our Sun moves calmly along its orbit, influenced by the combined gravitational pull of the galaxy's mass. It is far from the center, so the black hole's influence on our motion is gentle. But the stars near Sagittarius A experience a far stronger pull. They reveal how gravity behaves on scales we cannot experience in our everyday lives. Their motion shows what happens when mass becomes concentrated into a region so small that normal behavior no longer applies. Instead of drifting slowly like stars in the outer regions, they rush along paths shaped by the curved space near a supermassive black hole. Their movement also shows that the center of the galaxy is far from empty. It is a crowded region filled with stars, gas, and dust. The black hole sits at the core, but it is surrounded by activity. This environment would be far too dangerous for planets or calm solar systems, but stars adapted to that region continue to live their lives, burn their fuel, and orbit the center. Their presence challenges the idea that black holes are regions of nothingness. Instead, they are part of dynamic environments where matter interacts with gravity in complex ways. The idea of stars dancing around an invisible center may sound unusual, but it reflects a simple truth about the universe. Not everything we see reveals its nature directly. Some of the most important forces work quietly, pulling, shaping, and guiding without producing light or sound. The stars near Sagittarius A help reveal that hidden influence. Their motion is visible, their paths are measurable, and through those paths a deeper picture emerges. The region closest to a supermassive black hole behaves in ways that don't match anything in ordinary experience. When people hear the term gravity well, it's easy to imagine a simple hole in the ground or a funnel-shaped depression that pulls things inward. But the environment near Sagittarius A doesn't resemble a hole in any ordinary sense, because it isn't a place where something sits at the bottom, waiting to catch anything that falls. There is no floor, there is no surface, there is no material boundary. Instead, space becomes curved in a way that forces everything nearby to move differently than it would in normal conditions. That curvature isn't a physical shape you can see or touch. It's the mathematical behavior of space itself changing under the influence of mass. To understand how unusual this is, it helps to start with everyday gravity. On Earth, gravity holds you to the ground. It pulls objects downward. It gives weight to everything around you. But Earth's gravity works through a familiar environment. The ground pushes back, surfaces stop your fall, pressure, friction, and structure create limits that define how objects behave. None of that applies near a black hole. There are no surfaces to push against. There is no stable structure that shapes movement. Gravity becomes the only significant influence. It acts on matter in a way that gives no resistance, no stopping point, and no recovery once something crosses a particular boundary. The region just outside the event horizon is the part where things become most unusual. From far away, gravity behaves the same way it always does. Objects orbit stably. Light travels in straight lines unless a massive object bends it slightly. But closer to the black hole, the bending becomes stronger. Light paths curve more sharply. Objects feel stronger pull. Speeds increase. Then, at a certain point, space is curved so intensely that nothing can travel outward once it crosses the boundary. That boundary is the event horizon. It isn't a wall or a surface. It's simply the limit at which the escape speed becomes greater than the speed of light. Once crossed, motion only continues inward. Even before reaching that limit, time itself behaves differently. According to relativity, strong gravity slows time relative to regions farther away. This isn't a metaphor, it's a measurable effect. Clocks near a black hole tick more slowly when compared to clocks positioned far from its influence. If you watched a clock orbiting near Sagittarius A, it would appear to run slightly slower than your own. The difference grows as the clock moves closer to the event horizon. For extremely close orbits, the effect becomes significant. From the perspective of the orbiting clock, everything feels normal, but to a distant observer, time near the black hole passes more slowly. This difference in how time moves is part of what makes the environment feel so unusual. You could imagine two identical objects, one far away and one close to the black hole. After a certain amount of time has passed, the closer object would have experienced less time than the distant one. This isn't hypothetical. It has been measured with clocks on Earth at different altitudes. Even a difference of a few centimeters can cause measurable differences in time when using extremely precise atomic clocks. Near a supermassive black hole, the effect is far more dramatic. One strange part of this environment involves the behavior of light. Light normally travels in straight lines unless gravity curves those paths. Near Sagittarius A, the curvature is strong enough that light emitted from matter passing by may orbit the black hole one or more times before heading outward. This creates a region called the photon sphere, where light can travel in circular paths around the black hole. These orbits aren't stable in the long term. A tiny disturbance will cause the light to either fall inward or escape outward. But the existence of such paths shows how unusual the environment is. Light itself becomes part of the motion shaped by the black hole's gravity. Matter behaves equally strangely. When gas or dust passes close to the event horizon, it doesn't fall inward immediately. It begins to swirl, forming a rotating structure often called an accretion flow. This isn't a perfect disk like the ones shown in dramatic illustrations. In reality, the flow is often uneven, clumpy, and affected by magnetic fields. As matter spirals inward, it heats up due to friction and compression. This heating produces energy, especially in the form of X-rays. In the case of Sagittarius A, the accretion flow is surprisingly faint because the black hole isn't feeding heavily. Only small amounts of gas occasionally drift close enough to heat up and produce short flares. But in more active systems, this heating can become so intense that the region outshines the rest of the galaxy. The idea of falling toward the event horizon creates a common question. What would you feel if you approached it? In ordinary terms, falling feels like something because the ground accelerates toward you, or you accelerate toward the ground, and air pushes against your body. None of that exists near a black hole. Falling towards Sagittarius A would not feel like falling at all until you reached a region where tidal forces become strong. Tidal forces are differences in gravity across an object's length. On Earth, tidal forces are too weak to affect you personally. The moon creates tides in the oceans, but it doesn't stretch your body. Near a black hole, tidal forces become much stronger. However, one surprising fact is that a supermassive black hole produces gentle tidal forces near the event horizon. Because the black hole is so massive, the gradient of gravity over a human-sized distance is small at that point. A smaller black hole would tear objects apart long before they reach the event horizon. But Sagittarius A's event horizon is large enough that objects could cross it without feeling immediate stretching. Only much closer to the singularity would the forces become extreme enough to break things apart. But no one crossing that boundary could ever communicate their experience back outward. From the outside, the event horizon is the final visible surface. Inside, motion continues inward with no path leading back out. Another curious effect involves how the approach appears to an outside observer. If you watched an object fall toward the event horizon, you would never see it cross. Instead, the object would appear to slow down as it approached the boundary. Light from the falling object would become increasingly redshifted, meaning it stretches to longer wavelengths. Eventually, the object would fade from view entirely. From your perspective, it would seem to freeze at the edge, gradually disappearing. But from the perspective of the object itself, time would feel normal. It would cross the horizon without noticing a specific moment where anything changed. The difference between internal experience and external perception is one of the most unusual outcomes of relativity. The concept of a gravity well with no flaw is tied to the idea that once inside the event horizon, all possible paths lead inward. Normally you can choose your direction. You can walk to the left, to the right, forward or backward. You can climb upward or descend downward. Inside the event horizon, the direction inward becomes as unavoidable as the direction down in a hole you cannot climb out of, except there is no surface below. The geometry of space itself changes so that every path, every direction, every possible movement leads closer to the singularity. This singularity isn't a physical object. It's a region where the known laws of physics break down. The equations of general relativity predict that matter collapses into a point of infinite density, but most physicists believe this description is incomplete. Quantum effects likely change what happens at extremely small scales. A complete theory of quantum gravity might explain what really occurs inside the event horizon, but such a theory doesn't yet exist. For now, the singularity represents the limit of our understanding. Outside the event horizon, the environment is still extreme but not beyond comprehension. Space is curved strongly, but not infinitely. Light bends but does not collapse into the singularity. Matter heats but remains in orbit. This transitional region is where the most interesting physics occurs because it shows the boundary between familiar gravity and the conditions where relativity dominates. Sagittarius A offers a unique environment for testing these ideas because it is relatively peaceful compared to more active black holes. The lack of heavy feeding allows astronomers to observe the gravitational influence without interference from bright emissions or chaotic jets. Magnetic fields near the black hole also play a role in shaping how matter behaves. These fields can twist, compress, and channel gas as it moves through the region. The interplay between gravity and magnetism creates complex patterns in the accretion flow. In some black holes, this interplay launches jets of particles that shoot outward at nearly the speed of light. Sagittarius A doesn't currently produce strong jets, but evidence suggests it may have done so millions of years ago. Traces of past activity remain in the structure of surrounding gas clouds. Understanding the physics near a black hole also helps refine our picture of how galaxies evolve. The energy released by matter falling into a black hole can heat surrounding gas and influence star formation. In more active galaxies, black hole activity can regulate how quickly stars form by blowing out gas or heating it to temperatures that prevent collapse. Even though Sagittarius A is quiet today, its past influence may have shaped the distribution of stars near the centre. One surprising insight from studying black holes is that they do not pull everything inward indiscriminately. Most matter near them stays in orbit. Only when something loses energy or interacts with other material does it spiral inward. This behavior explains why stars near Sagittarius A remain stable. They move quickly enough to avoid falling in. Their orbits reflect a balance between gravitational pull and their own velocity. This delicate balance creates some of the most precise natural clocks in the galaxy. By measuring their motion, astronomers can calculate the mass of the black hole and test predictions about how gravity works under extreme conditions. Thinking about the physics near the event horizon can feel distant from everyday life, but the principles behind it are the same ones that shape the motion of planets, moons, and even objects falling toward Earth. The difference lies only in scale. The stronger the gravitational field, the more pronounced the effects. Near Sagittarius A, those effects reveal themselves in ways that help refine theories about how the universe works. Considering all of this, the idea of a gravity well without a flaw becomes less mysterious. It isn't a hole in the traditional sense. It's a region where the structure of space changes in a way that prevents escape. It is not a destructive presence in the galaxy. It is part of the natural evolution of massive objects. It shapes the motion of stars and influences the structure of the galaxy without pulling everything inward uncontrollably. For most of human history, no one had any idea that something massive sat at the centre of the Milky Way. People looked up and saw the faint band of starlight stretching across the sky, a hazy shape that inspired stories but didn't reveal much about its structure. There was no reason to suspect that deep within that glow lay an object so heavy and so dense that light itself could not escape from it. Even when telescopes improved, and astronomers began charting the stars with greater accuracy, the core of the galaxy remained hidden behind dust and gas. Visible light couldn't pass through the thick clouds between us and the centre. It wasn't until new instruments and new ideas emerged that the path toward discovering Sagittarius A began to take shape. The first hints did not come from starlight or from detailed maps of the galaxy. They came from radio waves. In the mid-20th century, radio astronomy started revealing features in the sky that hadn't been noticed before. Radio waves can pass through dust more easily than visible light. When scientists pointed radio telescopes toward the center of the Milky Way, they found a bright source that didn't match anything known at the time. It wasn't a star. It wasn't a nebula. It wasn't shaped like any familiar object. It was compact and intense, suggesting that something unusual was there. This source would later be called Sagittarius A, and eventually Sagittarius Aeons, with the asterisk used to denote its most compact point. At first, the radio source was just a curiosity. It didn't immediately signal a black hole. The concept of black holes was still considered somewhat theoretical by many scientists, and the idea that a supermassive one might sit at the center of our own galaxy seemed extreme. But the data were difficult to explain in any other way. The radio source was too small and too energetic to be explained by ordinary stars. Something was producing a signal from a region so tiny that only a very compact object could fit inside. Even then, astronomers needed more evidence. Radio signals alone weren't enough to prove the existence of a supermassive black hole. The breakthrough required a new approach. Instead of looking for the black hole directly, scientists realized they could look for its influence on the objects around it. If something massive was sitting at the center of the galaxy, it would affect the motion of nearby stars. Those stars would move quickly and follow curved paths around whatever occupied the center. The idea was simple, but putting it into practice required technology that didn't yet exist. Infrared astronomy eventually provided the next piece of the puzzle. Infrared light is better at passing through dust than visible light. When telescopes capable of capturing infrared wavelengths improved, astronomers could finally see the stars near the galactic center. Many of these stars were bright, young, and surprisingly energetic. More importantly, they were moving. They didn't sit still in the sky like distant stars do from our point of view. Their position shifted noticeably over time. In a region where stars are densely packed, this kind of motion held valuable clues. teams of astronomers began measuring the positions of these stars year after year. It wasn't a quick process. The motion needed to be tracked carefully to distinguish orbital movement from random drift. But gradually patterns emerged. Stars followed predictable curves, not random wandering paths. The center of their orbits appeared to be a single point that emitted no visible light. The more precisely the data were measured, the clearer the picture became. Whatever lay at the core had to be extremely massive, millions of times larger than the Sun, and yet invisible. One of the most remarkable parts of this discovery was the patience required. Astronomers needed to watch some stars complete entire orbits. That meant tracking them for more than a decade. S2, one of the stars closest to the black hole, became the key. Its 16-year orbit provided the data necessary to calculate the mass of the central object with precision. When the star reached the closest part of its orbit, it sped around the center at incredible velocity. This motion confirmed that the gravitational pull had to be coming from something extraordinarily dense. By this point, the evidence had begun to converge. The behavior of the stars made sense only if an enormous compact mass occupied the center. No cluster of smaller objects could produce the same effect. A cluster would either collapse under its own gravity or shine brightly. The center remained dark. That darkness was part of the signature. The only thing that matched all the observations was a supermassive black hole. More advanced tools continued to refine the picture. Observatories such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii contributed precise measurements. Interferometry, a technique that combines the light from multiple telescopes, allowed for even sharper resolution. Each new observation confirmed the pattern: fast-moving stars, small orbital radii, and an invisible center point. The position of that center became known with increasing accuracy. It lined up precisely with the radio source Sagittarius A, linking the two observations into a single explanation. As technology grew more sophisticated, astronomers started testing additional predictions of general relativity near the core. When S2 made a close pass in 2018, its light shifted in frequency as it climbed out of the black hole's gravitational field. This shift matched Einstein's predictions. It wasn't a dramatic effect to the naked eye, but it was unmistakable in the data. The star's orbit also displayed a small forward shift after completing a loop. This precession, expected from relativity, added further confirmation. Everything about the star's behavior matched what should happen near a supermassive black hole. Another major milestone came from the Event Horizon Telescope, a collaboration involving observatories around the world. This network used a technique called very long baseline interferometry to create a telescope effectively the size of Earth. With such resolution, the EHT could capture the region immediately surrounding the event horizon of Sagittarius A. The final image released in 2022 showed a ring-like structure of glowing gas around a dark central region. The dark area represented the shadow of the black hole. Not the black hole itself, but the absence of light caused by gravity pulling in anything that passed too close. This image wasn't a photograph in the traditional sense, but a reconstruction based on measured signals. It aligned with predictions of how matter should behave near a black hole and how light should curve around its edge. Even before the EHT image, the evidence was overwhelming, but the image offered a direct look at the environment surrounding the event horizon, confirming decades of inference. No alternative theory fit the observations as cleanly or consistently. The shape of the shadow, the brightness of the surrounding material, the dynamics of the region, all matched the expected properties of a black hole millions of times more massive than the Sun. Alongside these direct observations, scientists also studied the larger-scale behavior of the galaxy. Spiral galaxies often contain massive central objects, and the Milky Way followed the same pattern. The relationship between galaxy mass and central black hole mass supported the idea that Sagittarius A played a role in shaping the structure of the inner region. The stability of stellar orbits, the density of stars in the central cluster, and the behavior of gas clouds all pointed to a central mass, far greater than any cluster of stars could produce. The discovery process involved many steps, each building on the last. No single observation proved the existence of Sagittarius A by itself. Instead, a combination of radio data, infrared imaging, orbital measurements, spectroscopic analysis, and advanced interferometry created a consistent picture. The invisible object at the center wasn't just heavy, it was too heavy and too compact to be anything else. The idea that something so large and so influential could remain unseen for so long highlights how limited our natural senses are. Without specialized tools, the core of the galaxy would remain a mystery. Dust blocks the view, gas obscures the light. The black hole itself emits no visible signal. Everything we now understand about its existence comes from looking beyond the limits of human vision. It required instruments capable of reading signals across wavelengths we don't naturally detect. It required mathematical models to interpret motion we cannot see by eye. And it required decades of patient observation. One important part of the discovery is that Sagittarius A didn't make itself known through dramatic bursts or violent events. It wasn't actively feeding on large amounts of matter. It wasn't emitting strong jets or intense radiation. Many of the black holes discovered in distant galaxies were found because they shone brightly as active galactic nuclei. Sagittarius A, by comparison, was quiet. Its calm behavior made the discovery more challenging but also more meaningful. Instead of relying on bright emissions, astronomers had to focus on the subtle influence of gravity alone. That subtlety allowed for incredibly precise measurements of relativity and action. The center of the Milky Way became a natural laboratory. Instead of needing artificial experiments, the galaxy provided stars that acted as test objects. Each orbit offered a chance to check theoretical predictions. Each flare of gas near the event horizon offered a chance to study how matter behaves under extreme compression. Even silence in certain wavelengths revealed information. If Sagittarius A were something other than a black hole, it would produce different signals. Its quietness was not the absence of information. It was a defining characteristic. The road to understanding the central mass also benefited from comparisons to other galaxies. As more supermassive black holes were identified in distant galaxies, the pattern became harder to ignore. The correlation between galaxy size and black hole size looked consistent across many systems. The Milky Way fit the pattern neatly. It wasn't an exception, it was typical. That consistency reinforced the idea that the center of the Milky Way should contain a supermassive black hole shaped by the same processes that formed others across the universe. Even though the discovery involved many complex steps, the conclusion is surprisingly simple. If you take all the evidence and place it side by side, the radio source, the infrared motions, the relativistic effects, the orbital velocities, the stability of the central region, and the image from the Event Horizon telescope, they all point in the same direction. They describe a massive, compact object with no visible surface, exerting a gravitational force that only a black hole could produce. And yet, despite these discoveries, the center of the Milky Way remains a quiet place from our perspective. We cannot see it with our eyes. If you look up at the night sky, the region where Sagittarius A sits appears as a faint, hazy band of stars. You cannot sense its influence directly, even though it plays a role in shaping the entire structure of the galaxy. The discovery of Sagittarius A isn't a dramatic story about something erupting into view. It's a story about learning to look more carefully, using tools that extend our reach, and following small clues that eventually reveal something enormous. This gradual uncovering feels different from many scientific discoveries. It wasn't a sudden revelation. It was a slow accumulation of data, patiently measured over decades. It's a reminder that some truths in the universe are not obvious. They sit behind layers of darkness, waiting for the right tools and the right questions to make them visible. The stars nearest to the center of the Milky Way move with a kind of speed that's difficult to relate to everyday experience. They aren't drifting slowly around the galaxy the way our sun does. They aren't meandering through space in long, leisurely arcs. They are racing. Each one follows a path defined by the overwhelming mass of the object at the centre, responding to gravity so strong that even the smallest shift in position can create dramatic changes in velocity. These stars don't simply orbit. They accelerate and swing in ways that show just how extreme the environment near Sagittarius A really is. When astronomers first realized how quickly these stars move, it changed the entire discussion about the core of the Milky Way. Until then, people suspected there might be a massive object hidden there, but the specific motions of the stars confirmed just how dense that central mass must be. It's one thing to infer the presence of a black hole from radio signals or obscured light. It's another to watch stars whip through space at thousands of kilometers per second, something no cluster of smaller objects could cause without collapsing into a black hole. The speeds involved are almost beyond scale. Some of the stars travel so fast that they cover the distance between Earth and the Sun in just a few hours. If you could somehow stand near them, though in reality no one could survive the radiation or environment, you would see motion that feels out of place in the universe. Stars that normally seem fixed and stable would streak across the sky. From our vantage point on Earth, we see only small changes in position, but those small changes reflect enormous distances and extraordinary speeds. Seeing these motions in infrared data is like watching a dance sped up far beyond normal pacing, each movement revealing more about the hidden center they orbit. Among these stars, one in particular has become the most famous, the star commonly referred to as S2. Its orbit around the central mass has been tracked for decades. Because it completes a full loop in a little over 16 years, astronomers have been able to observe it moving through every part of its path. This kind of complete orbit is incredibly valuable because it allows scientists to measure not just the star's position, but how it accelerates, how it slows, and how its velocity changes as it swings near the black hole. Every part of that motion reflects the gravitational influence of the central mass. When S2 approaches the closest point in its orbit, it reaches speeds of about 8,000 kilometers per second. That's fast enough to travel from Earth to the Moon in less than a minute. Even though this motion is extreme, the star remains intact because its distance from the black hole is still far enough to avoid being torn apart by tidal forces. The balance between the star's velocity and the black hole's gravity creates a situation where the star swoops inward, reaches a critical point, and then slingshots back outward into the wider part of its orbit. Watching this motion confirms the mass of the black hole with remarkable precision. S2 isn't the only star with such a dramatic orbit. Several others move in equally interesting ways. Some have wider paths, some move faster or slower depending on their distance from the centre. A few stars orbit so close to Sagittarius A that they complete their paths in only a few years, moving at speeds that exceed anything found in the outer galaxy. Each one provides a slightly different angle of insight. Together they form a network of natural test particles that map the gravitational landscape of the central region. The variety in their orbits is part of what makes the area so fascinating. Unlike the planets in our solar system, these stars don't move in a single plane. Their orbits are tilted in many different directions. They don't line up neatly or form organized rings. Instead, they move through three-dimensional space in a pattern that looks chaotic at first glance. But underneath that apparent complexity is a consistent rule. Each star follows the curvature of space shaped by the black hole's mass. Their orbits intersect only in projections onto the sky. In actual space, they remain separated and stable. The stability itself is another interesting point. For something as extreme as a supermassive black hole, one might expect the environment to be chaotic or destructive. But the stars maintain their paths over long periods. They don't collide. They don't spiral inward uncontrollably. They don't veer off wildly. They follow predictable curves determined by gravity. Even the fastest stars adhere to stable orbits, unless they interact with gas clouds or other stars. This orderliness contradicts the common idea that the region around a black hole must be violent. Instead, it shows how gravity, even in extreme environments, can create stability when objects have the right velocity and distance. Some of these stars move unusually fast, not because they're close to the black hole, but because they were once part of systems disrupted by interactions near the centre. This can lead to what are called hypervelocity stars, objects flung out of the galactic centre at extraordinary speeds after gravitational encounters with the black hole. While these stars eventually escape the core and travel outward through the galaxy, the ones that remain near the centre continue orbiting along paths determined by the mass they circle. Those staying in the core region are the ones most useful for studying how gravity behaves near Sagittarius A. Another aspect that intrigues astronomers is the age of these stars. Many of them are surprisingly young. Under normal conditions, star formation in a region so close to a supermassive black hole should be difficult because of the strong gravitational forces and the turbulent environment. The gas clouds needed to form stars would have trouble remaining stable long enough to collapse, and yet there they are, young, bright stars moving rapidly around the black hole. One explanation is that these stars formed farther away and gradually migrated inward. Another suggests that at certain times, compressive forces in the region allowed star formation to occur despite the harsh environment. Whatever the origin, their presence adds complexity to the picture. Tracking these stars requires a combination of precision and patience. The movement from year to year is subtle on the sky, but instruments with high resolution can detect these shifts. Infrared telescopes provide the necessary clarity. Over decades, these repeated measurements create detailed maps of the star's paths. Each map tells part of the story. The faster the star, the more dramatic the curvature. The smaller the orbit, the closer the star comes to the black hole. Combining these details allows scientists to refine the mass estimate of Sagittarius A, confirm predictions of general relativity, and explore how the gravitational environment affects motion. Beyond the fast orbits themselves, scientists also study how these stars interact with the gas and dust near the centre. As they move, their radiation affects the surrounding material. Gas clouds can become compressed or heated as stars pass nearby. These interactions help reveal the density of the environment and the distribution of matter. In some cases, the stars may even disturb small amounts of gas that drift close to the black hole, contributing to the occasional flares observed in X-ray or infrared wavelengths. The speed of the stars also helps illustrate a point about black holes that can be counterintuitive. Although Sagittarius A is 4 million times more massive than the Sun, it influences objects most strongly only when they are very close. Farther away, the gravitational pull feels similar to that of any massive object. The stars that orbit fast are located in the region where the black hole's gravitational effects dominate over the influence of the surrounding mass. As soon as you travel farther outward, the combined mass of nearby stars and gas becomes equally important. The black hole's pull weakens with distance, just like any gravitational force. Even so, the stars near the centre serve as visible evidence of the black hole's existence. They show something that cannot be observed directly but can be inferred from their motion. When a star curves that sharply around a point that emits no light, there's only one explanation that fits the data. These stars act like markers drawing the outline of a shape we cannot see. Their paths reveal the central mass more clearly than any image could. Even though the black hole remains invisible, the motion of the stars makes its presence unmistakable. The incredible speeds also demonstrate something important about the nature of energy in these environments. Objects in orbit have a balance of kinetic and potential energy. The closer they move toward a massive object, the more potential energy is converted into kinetic energy. That conversion produces the rapid motion observed near the centre. When they swing outward again, that energy redistributes, slowing them down naturally. This continuous exchange echoes the familiar motion of comets in our solar system, which speed up near the Sun and slow down as they move away. The difference near a black hole is simply the scale. The gravitational pull is much stronger, the velocities are much higher, but the principles remain the same. All of this motion creates an environment that seems intense from a human vantage point, yet to the stars involved, it's just the behaviour dictated by gravity. They don't feel the speed in the way humans would, because motion in space doesn't involve friction or wind. Their orbit doesn't stress their structure the way high speed would for objects on Earth. They simply follow their paths, completing loops around the centre again and again, each one a predictable response to the black hole's mass. What makes this even more striking is how these motions appear when plotted over decades. A single photograph of the central region might not reveal much, but when you overlay years of positions, the curves become obvious. The orbits look like loops traced by a careful hand. The precision of these curves is what convinced so many scientists that they were observing the effects of a single massive object, not a cloud of smaller objects. The central mass must be dense enough to fit within the boundaries traced by the innermost stars. This density requirement rules out most alternatives. Only a black hole fits. These orbits also help test fundamental physics. General relativity predicts that the paths of stars near a massive object will change slightly over time. This change is subtle but measurable. Observing it helps confirm or refine the theory. The stars near Sagittarius A have become important tools for studying gravity under conditions that cannot be reproduced in a laboratory. Their behaviour teaches us how space curves and how objects respond to that curvature. Seeing these stars moving with such speed and precision offers a reminder of how dynamic the universe is. From Earth, the night sky seems fixed and stable, with stars appearing to stand still, but in reality stars move constantly. It's just that in most places the movement is too slow for the human eye to detect. Near Sagittarius A, the movement is fast enough to watch unfold over the course of years. This view reveals a part of the galaxy's life that remains hidden from casual observation. The closeness of these stars to the black hole also gives clues about how the region evolved. Stars don't form easily in such extreme environments, so their presence suggests either migration or a special set of conditions in the past. Understanding how they arrived helps scientists piece together the history of the core. Their ages, motions, and distribution all contribute to reconstructing the timeline of events near the centre. Although humans will never be able to witness this region firsthand, the data collected over decades create a picture that feels almost tangible. The idea of stars rushing along tight curves around an invisible object shows how much is happening in areas we cannot see directly, and that picture becomes clearer with every new observation. More precise instruments allow for more detailed measurements. Longer time baselines reveal more about how orbits evolve. Future observations will continue refining our understanding. Seeing into the centre of the Milky Way was impossible for most of human history. People could look at the sky on a clear night and notice the faint band of stars stretching overhead, but that view gave no hint of what lay behind the glow. The dust and gas filling the plane of the galaxy act like a curtain that blocks visible light, preventing even the most powerful early telescopes from reaching the core. For centuries, the centre remained a region we could only imagine. There was no way to see through the haze, no hint that something massive and unseen occupied the heart of the galaxy. The discovery of what existed there required new tools, telescopes sensitive to wavelengths that don't behave the way ordinary light does. The first major change came with radio astronomy. Before radio telescopes, the sky was explored almost entirely through visible light. Once scientists learned to build instruments that could detect radio waves, the universe looked very different. Radio waves aren't disturbed by dust the way visible light is. They can move through the thick clouds blocking our view, carrying signals that reveal structures hidden from ordinary vision. When one of the early radio surveys of the sky pointed toward the centre of the Milky Way, astronomers saw something unexpected, a bright compact radio source that didn't match any known object. This source was labelled Sagittarius A. No one knew what it was at first, but it became clear that it wasn't an ordinary star. As radio astronomy developed further, scientists began mapping the sky in detail, charting where radio emissions were strongest. The core of the Milky Way stood out as a complex region filled with signals. Some of them came from supernova remnants, some came from clouds of ionized gas. But one particular point near the centre remained unusually compact, emitting radio waves with a profile that indicated something dense and energetic. It wasn't large, it wasn't spread out like a nebula. It was a single concentrated point. Eventually this point was named Sagittarius A, the asterisk marking it as a unique component. Even with that identification, its true nature was still unknown. The presence of radio waves didn't confirm a black hole, but it planted a seed. Radio telescopes alone weren't enough. They provided an early map, but astronomers needed to see the stars moving around the source. That required infrared observations, light beyond the red end of the spectrum, with wavelengths long enough to slip through the dust. Infrared astronomy existed in principle, but for much of the 20th century, the instruments weren't sensitive enough to capture detailed images of the galaxy's core. Detectors gradually improved, and with each advancement the picture became clearer. When the first high-resolution infrared observations of the central region were made, scientists finally saw the stars that had been hidden behind the dust. These stars were not evenly spaced or slow-moving. They were concentrated, bright, and clearly influenced by something massive nearby. But the resolution needed to track their movement over time remained limited. The next step involved building telescopes capable of resolving extremely small details. Interferometry became essential for this. Instead of relying on a single telescope, interferometry combines the light from multiple telescopes spread across a wide distance, effectively creating one giant instrument. This technique increases resolution far beyond what any single telescope can achieve. 2 observatories became central to studying the core in this way: the Very Large Telescope, VLT in Chile, and the Keck Observatory in Hawaii. Both had powerful infrared capabilities, and both used interferometric methods to achieve the necessary sharpness. When these facilities began systematically observing the centre year after year, astronomers could finally track how specific stars moved over time. Each shift in position, each curve in the path, revealed more about the gravity pulling on them. The key was consistency. Observations had to be made regularly over decades. The motion was fast compared to stars far from the centre, but still slow enough that careful measurement was essential. Year by year, astronomers watched as stars traced arcs in the sky. Some completed noticeable fractions of their orbits. Others sped through narrow paths near the centre. As data accumulated, computers began plotting the trajectories with increasing accuracy. It became obvious that these orbits did not point to a cluster of smaller objects. A cluster would be too unstable, too luminous, or too large. The gravitational pull needed to explain the star's motion required a compact mass that only a black hole could provide. Even with infrared and radio observations, the view still wasn't complete. The environment near a black hole also emits X-rays, especially when gas heats up as it spirals inward. X-ray telescopes orbiting Earth gave additional clues about the behaviour of matter near Sagittarius A. Instruments like NASA's Chandra X-ray Observatory detected occasional flares from the region. These flares were small compared to those from the active supermassive black holes in distant galaxies, but their patterns matched the expected behaviour of gas falling toward a black hole. The fact that the core wasn't constantly bright indicated the black hole was quiet, not feeding heavily, which matched what infrared observation suggested. Meanwhile, Earth-based observatories continued improving. Adaptive optics became one of the most important developments. When light from distant stars passes through Earth's atmosphere, turbulence in the air distorts the image, causing stars to twinkle. For astronomical observations, that twinkle represents lost detail. Adaptive optics systems use rapidly adjusting mirrors to cancel out the atmospheric distortion in real time. With these systems, telescopes like Keck and the VLT could capture sharper images of the galactic centre than ever before. This improvement made it possible to see details that had been invisible just a decade earlier. Star positions could be tracked to astonishing precision. The shape of their orbits became clearer. Differences in speed from one year to the next were measurable. Infrared images revealed how the stars crowded near the center, forming a dense cluster that required a central mass to keep it stable. Without the advances in adaptive optics, the motion would have been too blurred to detect. While these ground-based telescopes provided most of the detailed motion tracking, another type of instrument contributed a different kind of insight. Radio interferometry spread across continents allowed for extremely fine resolution at radio wavelengths. The Very Long Baseline Array, VLBA, which links radio antennas thousands of kilometers apart, gave astronomers the ability to pinpoint the location of Sagittarius A with extraordinary precision. Every measurement confirmed that the radio source and the central mass inferred from star orbits occupied the same position. That alignment strengthened the argument that both observations pointed to the same object. Then came one of the most ambitious projects in observational astronomy, the Event Horizon Telescope. This international array of observatories linked telescopes around the world to form a virtual Earth-size radio dish. The goal was to image the region immediately surrounding a black hole's event horizon. Achieving this required synchronizing telescopes separated by thousands of kilometers with atomic clock precision. Each observatory collected data during carefully coordinated observing runs, and then massive computing power combined the signals into a single image. The first major achievement of the EHT was imaging the black hole at the center of the galaxy M87. The famous glowing ring surrounding a dark center showed what the environment around a supermassive black hole looks like at extremely high resolution. After that, the attention turned to Sagittarius A. The Milky Way's central black hole presented additional challenges. It's much smaller than the one in M87, meaning matter moves more quickly around it. That fast motion made the imaging process more difficult because the ring changes on short timescales. Even so, after years of effort, the EHT released the first image of Sagittarius A in 2022. The image wasn't a photograph in the traditional sense. It was a reconstruction based on data processed through complex algorithms. But what it showed matched expectations: a glowing ring of heated gas surrounding a dark region where light couldn't escape. The size of the ring matched what general relativity predicted for a black hole of 4 million solar masses. This result didn't replace the earlier evidence, but it added a powerful piece to the puzzle. It showed the outline of the black hole's shadow, the region where light paths curve inward and vanish. Even though the EHT image looked blurry compared to typical astronomical photos, it represented a level of detail that was impossible to achieve just a few years earlier. It came from telescopes acting together across continents. This kind of coordination wasn't just a technical achievement. It demonstrated how much progress has been made in observing objects that emit no visible light. A century ago, the very idea of imaging a black hole would have seemed unimaginable. Now, through careful calibration and processing, the structure near the event horizon can be studied in real detail. Each advancement in telescope technology added a different layer of understanding. Radio telescopes revealed the presence of a compact source. Infrared telescopes showed stars moving in curved paths. Adaptive optics sharpened the images. Interferometry increased resolution. X-ray telescopes detected flares from hot gas. The EHT imaged the region immediately around the event horizon. None of these instruments alone would have been enough. Together they built the full picture. One of the remarkable things about these telescopes is how they extend human senses far beyond natural limits. The human eye cannot see infrared or radio waves. It cannot detect X-rays or resolve tiny shifts in star positions. Telescopes that operate at these wavelengths act like new sense organs, revealing a universe that differs entirely from what our eyes perceive. Without them, the center of the Milky Way would still be an empty patch in the sky. The black hole would remain unknown. The fast-moving stars would be hidden behind dust. The flares from gas clouds would go unnoticed. All the structure, all the motion, all the evidence would remain invisible. It's easy to think of telescopes as tools for magnifying distant objects, but in reality they are far more than that. They transform signals that would otherwise never reach us into images and measurements that can be analysed. They allow us to observe parts of the electromagnetic spectrum that our eyes cannot detect. They provide clarity through layers of dust that would block conventional views. They fill in the gaps that natural limitations leave behind. The path to understanding Sagittarius A wasn't just about building bigger telescopes. It was about building telescopes smarter than those before them. Telescopes that compensate for atmospheric distortion, that work together across oceans, that measure wavelengths beyond human perception, that rely on computational models to reconstruct images where raw observations aren't enough. Every improvement opened a new window into the darkness. This steady progression also demonstrated something essential about science. Discoveries rarely happen in isolation. Understanding the center of the Milky Way required collaboration across decades, across continents, and across fields. Astronomers, engineers, computer scientists, and instrument designers all contributed to the tools that made the discovery possible. Each technique built on the ones before it, gradually revealing the structure hidden behind the dust. As these telescopes continued to gather data, the picture of the galactic center became more detailed and more consistent. The stars continued to follow their curved paths. The position of the radio source remained fixed. The flares behaved like gas falling toward a black hole. The EHT image matched theoretical predictions. All the details fit together. The instruments didn't just confirm the presence of a black hole, they allowed scientists to study it, to measure it, to test theories against it. Sagittarius A went from being an unknown region to one of the most studied objects in the galaxy. When you think of the Milky Way as a whole, it's tempting to imagine it as a quiet, static painting stretched across space. The spiral arms, the glowing clusters, the dark lanes of dust, they look serene when shown in pictures. But the galaxy isn't still. Everything moves. Stars drift in long paths that take hundreds of millions of years to complete. Gas clouds spiral inward or outward as gravity shapes their motion. Dark matter forms a halo around the visible disk, providing extra mass that holds the entire structure together. At the center of all of this motion sits the supermassive black hole, hidden behind dust but exerting a gravitational influence that helps set the pattern for the entire system. It's important to understand that the black hole doesn't act like a conductor in the literal sense. It doesn't direct each star individually or oversee the galaxy like some kind of manager. Instead, its presence contributes to the overall gravitational balance that shapes the motion of everything around it. The word symmetry might suggest that the galaxy moves in a perfectly choreographed way, but the reality is more like a natural arrangement that emerges from the distribution of mass. The stars, the gas, the dark matter, and the black hole all play roles in establishing this balance. Gravity simply responds to where mass is located, and over time, a pattern emerges. Near the center, the influence of the black hole is strongest. That much is clear from the fast orbits of the stars in the core. But farther out, the black hole's influence blends with the mass of the stellar bulge, a dense spherical region of stars surrounding the center. The bulge contains far more mass than the black hole itself, and together they shape the gravitational potential that governs the inner galaxy. The combination of the bulge and the central black hole forms the region where gravity is strongest, where stars move in tight loops and gas flows in complex patterns. As you travel outward from the center, the dense bulge gradually gives way to the thicker part of the disk. The spiral arms take shape in this region. These arms aren't structures like rigid spokes on a wheel. They're patterns formed by density waves, areas where stars and gas concentrate temporarily as they orbit. Think of them as traffic patterns on a highway. Cars move through them, slowing down or speeding up depending on congestion. In a galaxy, stars pass through the spiral arms as they orbit, spending more time in them because the density is higher. The arms themselves are shaped by the overall gravitational field, which includes the mass of the black hole at the center. Even though the black hole isn't pulling on each star individually in the outer disk, its contribution to the central mass affects the gravitational potential, that defines how fast stars must move to remain in orbit. Stars farther from the center need to move at certain speeds to maintain stable paths. If the central mass were different, the speeds required for stable orbits would change. A missing central mass would alter how tightly the inner regions bind together, which would, over long timescales, affect the pattern of the spiral arms and the overall structure of the galaxy. This is part of what makes the black hole's role so interesting. It doesn't dominate the galaxy. It doesn't hold it together by itself, but it contributes to the structure in a way that affects the long-term evolution of the Milky Way. Without a supermassive black hole in the center, the distribution of mass would be different, and the motions of stars in the inner region wouldn't match the observed pattern. Galaxies with heavier black holes tend to have denser inner regions. Galaxies with lighter central masses have different core structures. Sagittarius A fits neatly into the category expected for a galaxy of the Milky Way's size, suggesting the two evolved together. One way to visualize this influence is to picture a spinning disk with a heavy ball placed at its center. The ball doesn't force each piece of the disk to move, but its presence affects the balance of the spinning structure. The disk stabilizes around the heavy central mass, and the motion becomes more uniform. Remove the ball, and the disk loses some of that stability. The spiral arms might shift or weaken over time. In the Milky Way, the black hole and the bulge act together as that central weight. The central region isn't just a dense cluster of stars, it's also filled with gas clouds moving in various directions. Some clouds fall inward, others rise away from the plane of the galaxy. Some rotate too slowly to maintain stable orbits, some rotate too quickly. Over long periods, interactions among these clouds produce shock waves, pressure changes and star formation events. All of this motion feeds back into the larger structure of the galaxy. The black hole plays a role in this environment not by pulling everything inward, but by shaping the gravitational landscape in which these clouds move. On top of this, the distribution of dark matter influences the gravitational field even more strongly than visible matter. Dark matter forms a halo around the galaxy, extending far beyond the visible disk. Its mass affects how fast stars in the outer regions orbit. Without dark matter, the outer parts of the galaxy would not rotate fast enough to remain stable. But even with all that extra mass, the central black hole still contributes meaningfully to the gravitational shape of the inner region. It might seem surprising that something relatively small in mass compared to the entire galaxy can have such influence. The Milky Way contains hundreds of billions of stars. It contains immense amounts of gas and dust. It contains an even larger amount of dark matter. The black hole's 4 million solar masses are only a tiny fraction of the total mass. But its position at the very center gives it a unique role. The gravitational potential of a galaxy is shaped not just by the total mass, but by how that mass is distributed. Because the black hole sits at the exact center, its mass affects the deepest part of the gravitational well. This core region shapes the strength and stability of the inner galaxy. The interplay between the black hole and the surrounding stars helps maintain this structure over billions of years. Stars near the center orbit quickly enough that they rarely fall inward. Instead, they trace paths that reveal the shape of the gravitational field. These orbits stabilize the distribution of stars near the core. The black hole's presence ensures the gravitational field remains compact enough to prevent the inner region from becoming too diffuse. If the central mass were smaller, the distribution of stars near the core would look different. Another factor influenced by the black hole is the behavior of gas in the central region. Gas clouds follow more complicated paths than stars because they can collide, compress, and heat up. When gas moves through the gravitational potential, it forms structures such as rings, spirals, or streams. The specific shape of these structures depends on the central mass. For example, the Milky Way has a central molecular zone, a dense ring of gas orbiting in the inner few hundred light years. The dynamics of this zone are shaped in part by the presence of the black hole. Gas that drifts too close may be heated or stretched. Gas that stays farther out may collapse into new stars. This ongoing cycle affects how the inner galaxy evolves. Over millions of years, these processes create a pattern of motion that links the outer disk to the inner core. Gravity sets the pace. Stars in the inner galaxy move faster because the gravitational pull is stronger there. Stars in the outer galaxy move more slowly. But because dark matter increases the gravitational force at greater distances, the orbit speeds don't decrease as quickly as they would in a simple system. The result is a rotation curve, how speed changes with distance, that is relatively flat. This flatness was one of the first major clues that dark matter exists. Even with dark matter contributing most of the mass, the black hole still shapes the inner part of the curve. Farther out, where the spiral arms are most visible, the influence of the black hole fades into the background, but it never disappears entirely. Stars there still orbit the center, and the center still includes the black hole. Over the very long timescales of galactic evolution, subtle effects accumulate. A slightly different central mass could shift the rate at which the spiral arms wind around the galaxy. It could alter the alignment of bar structures, long, straight features sometimes found in spiral galaxies. The Milky Way has a bar as well, stretching across the central region. Bars often help move gas toward the core, where it can form stars or fall into the central black hole. The existence of the bar itself suggests a connection between the black hole and the motion of the galaxy's inner structure. One of the most interesting aspects of galactic motion is how stable it remains over enormous spans of time. Galaxies aren't fragile. They don't fall apart just because stars move at different speeds. The combined gravitational influence of the mass keeps everything in place. Collisions between stars are incredibly rare because the distances between them are so vast. Instead, what changes over time are the large-scale patterns, how the spiral arms rotate, how the bar evolves, how gas flows in or out of the core. All of these changes happen slowly compared to human timescales, but the presence of the black hole contributes to the long-term stability. Sagittarius A's influence also extends into the vertical thickness of the galactic disk. The disk isn't perfectly flat. It wobbles slightly and has a certain thickness caused by the velocities of stars above and below the galactic plane. The gravitational pull of the central mass helps create the restoring force that keeps the disk from becoming too thick or too thin. Without that central mass, the vertical structure of the galaxy would change over time. The balance would shift and the disk could become less organized. It's tempting to imagine that the black hole's influence must be dramatic to matter, but its importance lies in consistency, not drama. It doesn't need to launch jets or devour massive amounts of gas to affect the galaxy. It simply needs to exist as part of the mass distribution that shapes the gravitational potential. That potential determines how matter moves, how stars orbit, where gas collects, and how structures form. Over vast stretches of time, these motions settle into a pattern that persists. From Earth, it's impossible to see this pattern in motion. Our lifespan is too short, the changes are too slow, the galaxy is too large. But when scientists map the motions of stars across the Milky Way, they see the signature of rotation everywhere. Stars move in coordinated ways shaped by the center. Gas flows along curves influenced by gravity. Even streams of stars torn from ancient clusters trace arcs set by the galaxy's gravitational well. All of these motions point inward, not toward a bright beacon, but toward a dark, quiet region where the mass of millions of suns sits compressed into a space hidden from view. The idea of a symphony might suggest something performed intentionally, but in this case the music comes from the natural laws of motion. Mass shapes space, space shapes motion, motion reveals the mass. The black hole, the bulge, the stars, the gas, and the dark matter all contribute to this arrangement. The central black hole simply occupies the point where the gravitational potential is deepest. It anchors the structure by being part of the weight at the center. Without it, the galaxy would not fall apart, but its shape and motion would be different. The region just outside the event horizon of a black hole is one of the strangest places in the universe, not because anything magical happens there, but because the rules that normally guide how time and space behave begin shifting in ways that are unfamiliar to everyday experience. The physics doesn't break. It simply follows the math of general relativity, which predicts how mass bends the structure of space and how time flows differently depending on the strength of gravity. At the edge of Sagittarius A, these effects become so pronounced that they create an environment where time itself noticeably slows down compared to regions farther away. From far out in the galaxy, everything near the event horizon behaves in a predictable way, but the behavior no longer matches the intuition built from living in a world where gravity is relatively weak. For most of our daily experience, time seems steady. Clocks tick at the same pace regardless of where you are on Earth, but even on our planet, gravity affects time. A clock on the ground runs ever so slightly slower than a clock placed a few meters higher, because the one higher up is in a slightly weaker gravitational field. That difference is tiny, far too small to notice without extremely precise measurements. Near a supermassive black hole, however, the effect becomes significant. Imagine you're observing an object falling toward the event horizon of Sagittarius A. As it gets closer, the gravitational pull increases, and the curvature of space becomes more extreme. From your position far away, you would see the object's clock running slower than your own. If the object had a signal that ticked once per second, you would see the ticks gradually stretch apart. 1 second would become 2, then 3, then more. As the object approached the event horizon, the time between ticks would increase until the signal slowed to a crawl. From your perspective, the object would never actually cross the event horizon. It would approach the boundary indefinitely, fading as the light it emitted stretched into longer wavelengths. But that slow approach is only an illusion caused by the way light travels through curved space. The object itself would not experience anything unusual. His own sense of time would remain normal. It would not feel like time slowed. It would simply continue moving until it crossed the event horizon, unaware of any boundary. The event horizon has no physical surface or barrier. It's simply the location where the escape velocity exceeds the speed of light. From the object's perspective, nothing remarkable marks that moment. The laws of physics continue as they always did. The difference is only in how others perceive its motion. This discrepancy between the internal and external experience is one of the most striking aspects of relativity. It shows how time is not absolute. It depends on where you are and how fast you're moving. Near a black hole, time slows significantly for objects close to the event horizon relative to those farther out. This slowing is not due to any change in the object's internal processes, but because the geometry of space-time changes in a way that affects how time flows. Even light feels this effect. When light travels upward out of a gravitational well, it loses energy. This loss doesn't slow the speed of light, but it shifts the light's wavelength. Light emitted from near the event horizon appears redder when observed from afar. This effect is called gravitational redshift. In extreme cases, the light stretches so far into long wavelengths that it becomes undetectable. That's one reason falling objects appear to fade before they disappear. Their light stretches to wavelengths that instruments can no longer detect. Matter behaves in equally unusual ways as it approaches the event horizon, but not all matter plunges inward immediately. Much of it enters a kind of holding pattern, spiraling around the black hole before slowly drifting closer. This movement forms what scientists call an accretion flow. In the case of Sagittarius A, the accretion flow is relatively weak because the black hole isn't consuming large amounts of material. But when small pockets of gas approach the event horizon, they can heat up significantly. That heating creates brief flares observable in infrared or X-ray wavelengths. These flares offer clues about how matter behaves near the edge where time slows dramatically. The heating occurs because the matter compresses and rubs against itself as it spirals inward. Magnetic fields also play a role, twisting and pulling the gas in unpredictable ways. As matter heats up, it emits radiation. When astronomers observe these flares, they can sometimes track how the brightness changes. These changes happen over minutes or hours and reveal how motion near the event horizon unfolds at incredible speeds. Yet even with such motion, the falling matter appears to slow down as it approaches the boundary, because the signals it sends outward stretch and fade due to gravitational time dilation. If you imagine being near the event horizon yourself, the environment would appear different from what people often expect. The tidal forces, differences in gravity between your head and your feet, would be surprisingly gentle at the event horizon of a supermassive black hole. That's because tidal forces depend on how quickly gravity changes with distance. In smaller black holes, that change is rapid, and falling objects would be stretched and torn long before reaching the event horizon. But in a supermassive black hole like Sagittarius A, the gravitational gradient is much weaker at the boundary. You could cross the event horizon without feeling immediate effects. Inside, however, tidal forces eventually become extreme as distance to the singularity shrinks. The behavior of light around the black hole also adds to the strangeness. Because space is so curved near the event horizon, light can orbit in unstable loops. There is a region where photons can travel in circular paths. This area is called the photon sphere. It isn't a solid shell or a visible feature. It's simply a location where the path of light curves so sharply that it can circle the black hole before escaping or falling inward. These orbits are unstable, so even a slight disturbance sends the photons either outward or inward. But the existence of this region shows how profoundly space is curved near the event horizon. The event horizon itself isn't a physical structure. Nothing stops at that boundary. It marks a change in what paths are possible. Outside the event horizon, you can move in any direction. You can fall inward or move outward if you have enough velocity. Inside the event horizon, all possible paths lead inward. No amount of energy or effort could point you outward. It would be like trying to move upward in a region where upward no longer exists. The geometry of space changes completely. That's why there is no floor to the gravity well. There's no bottom surface waiting. There's only a region where space curves so steeply that all directions lead deeper into the black hole. One interesting consequence of this is how the shape of the black hole's shadow forms. The shadow isn't the black hole itself. It's the region from which no light reaches an outside observer, because those photons are trapped by the curvature. This is what the Event Horizon Telescope imaged. The glowing ring around the shadow comes from hot gas swirling outside the event horizon. The shape of the shadow depends on the mass and spin of the black hole. Sagittarius A's shadow provides information about how the black hole rotates. The rotation affects the shape of space near the horizon, dragging it along slightly in a process called frame dragging. This effect is subtle but measurable. The rotation stretches the region around the black hole, making some paths curve differently than they would around a non-rotating mass. These interactions create a dynamic environment that is constantly changing, even if the black hole itself remains quiet. Small pockets of gas drift inward, heat up, flare, fade, and disappear. Magnetic fields twist and reshape the flow. The curvature of space bends light. Some photons escape outward after circling the black hole more than once. Others fall inward without being seen. All of this activity happens at the edge where time slows dramatically. For astronomers studying Sagittarius A, these effects aren't just theoretical curiosities, they are tools. By observing how light behaves near the horizon, scientists can test predictions of general relativity. By measuring how time dilation affects the signals from orbiting stars and falling gas, they can refine models of how gravity functions in extreme environments. The region around Sagittarius A becomes a natural laboratory, offering a kind of test environment impossible to reproduce on Earth. Even though the black hole is quiet, the physics around it remains active. The occasional flares help confirm the size of the event horizon. The timing of the flares reveals how matter moves near the boundary. Observations of the orbits of stars show how time dilation affects their motion. Some stars move so quickly that even small relativistic effects become noticeable in their paths. As technology improves, these details become clearer. The slowing of time near the event horizon is not a separate phenomenon. It's woven into the geometry of space. Gravity isn't a force pulling objects inward in the traditional sense. It's the curvature of space guiding their motion. Time is part of that curvature. When space curves strongly, time slows strongly. That slowing isn't something you feel. It's simply part of how the universe behaves on large scales. Near Sagittarius A, the effect becomes visible because the mass is enormous and the curvature is strong. The region near the event horizon also reveals something about the limits of our understanding. The theory of general relativity describes how time and space behave near a black hole, but it doesn't describe what happens at the singularity. Somewhere inside the event horizon, the predictions of relativity break down. Quantum mechanics should take over, but there is no complete theory that blends gravity and quantum physics yet. This gap in understanding makes the center of a black hole one of the most mysterious places in science. The event horizon marks the boundary of where our current theories work. Beyond that point, the equations no longer provide clear answers. Despite this uncertainty, the physics outside the event horizon remains predictable. The behavior of time, light and matter is well understood. Observations near Sagittarius match theoretical predictions with remarkable accuracy. Even the subtle details such as the redshift of starlight during close passages align with expectations. This agreement gives scientists confidence that their understanding of gravity is correct in this regime. What makes the edge of the black hole so compelling is how it blends the familiar and the extreme. The basic principles of motion still apply. Objects move according to their energy and the curvature of space. Light travels along the paths allowed by gravity. Time flows at a consistent pace locally. But when these principles combine under stronger gravity than what we experience on Earth, they produce effects that feel strange, only because our intuition wasn't built in an environment where gravity is that strong. Imagining this region helps highlight how the universe works on scales far larger than our everyday lives. It shows that even though the rules are the same, the outcomes look different when mass becomes concentrated in such a small space. That difference isn't a mystery, it's a predictable result of the equations describing relativity. The idea that a black hole swallows everything around it is one of the most common misunderstandings in astronomy. Popular images often show a swirling drain in space pulling in stars, planets, and gas from every direction. That image is dramatic, but it doesn't reflect how gravity actually works. A black hole doesn't vacuum everything nearby the way a household machine pulls in crumbs. It doesn't roam through the galaxy devouring matter. It doesn't tug at distant stars or planets with a force that grows mysteriously stronger the farther you are. Its gravity follows the same rules that every other massive object follows. The difference is simply that a black hole packs a huge amount of mass into a small region. Thinking of a black hole as a vacuum cleaner makes sense emotionally, because the name includes the word hole, and that word suggests an empty space that things fall into. But hole is just a label for a region where gravity becomes strong enough that not even light can escape. That region isn't a trap in the traditional sense. It doesn't pull things in from great distances any more than a star of the same mass would. In fact, if the Sun were quietly replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. The only major difference would be the absence of sunlight. Gravity wouldn't change. The planets wouldn't suddenly get dragged inward. Their motion would remain stable. Sagittarius A behaves the same way, scaled up to much larger mass. It doesn't pull the Milky Way inward like a drain. It doesn't rip stars from their orbits in distant regions. Stars remain where they are because they have the right velocity to stay in orbit. The simple rule is this: if an object is far enough away and has the right speed, it remains in orbit indefinitely. A black hole cannot reach across space and grab it. Its influence decreases with distance, exactly the way the influence of any massive object does. Gravity doesn't change its rules just because light can't escape from the core. The misconception comes partly from how dramatic artists' impressions often look. Illustrations of black holes typically show long streams of gas stretching inward, or disks of bright material spiraling tightly. These images show active black holes that consume large amounts of matter, but not all black holes behave this way. Sagittarius A is quiet by comparison. It consumes very little gas. Material near the core is sparse. Objects that fall inward usually do so after long periods, and only after losing energy through interactions with other matter. The region around Sagittarius A is mostly stable. One helpful way to understand this is to think about orbits. When something orbits a massive object, it's not being sucked in. It's falling and missing at the same time. The object moves forward quickly enough that even though gravity pulls it inward, it never reaches the center. It continually falls around the massive object, which is what an orbit is. Stars near Sagittarius A behave this way. They fall toward the center due to gravity, but their forward motion is fast enough to keep them moving around it. Their orbits are stable for long periods. They don't drift inward because nothing slows them down enough to make them lose energy. For an object to fall into a black hole, something has to remove its orbital energy. That can happen if it collides with another object, passes through dense gas, or interacts with the magnetic fields near the core. But these events are rare. Space is mostly empty. Stars are far apart compared to their sizes. Even in the crowded region near Sagittarius A, the chance of collision remains low. Most objects continue orbiting for millions or billions of years. It's helpful to imagine the space around the black hole as a kind of basin with different height levels, except the basin isn't a physical structure, it's the shape of the gravitational field. Objects in high orbits remain stable unless something gives them a push. If they remain where they are, they stay in orbit. Only objects that lose enough energy can move inward to lower orbits, and only objects that lose nearly all their orbital energy can cross the event horizon. The black hole doesn't actively pull them inward. They simply follow the rules of gravity. Most objects have orbits that remain far from the event horizon. Gas behaves differently from stars because gas molecules can collide. Collisions create friction and heat. This heating eventually causes gas to lose energy and spiral inward slowly. But the process is far slower than people often imagine. Gas clouds orbit for long periods before drifting inward. Even when they do, the gas doesn't fall straight in. It forms a rotating structure and moves inward gradually. The heat from these interactions produces flares, but the amount of matter involved is usually small. Sagittarius A's quiet nature shows how stable this process can be. The black hole at the center of our galaxy currently accretes only tiny amounts of gas. Most of the time, it emits no intense radiation. It's a sleeping giant, influencing the shape of the galaxy without aggressively consuming matter. Even during its active periods millions of years ago, it would have needed an abundant supply of gas to become bright. But that supply eventually thinned out. Now only small pockets drift inward occasionally. The calm nature of Sagittarius A is consistent with what astronomers see in many other galaxies. After the early phases of galaxy formation, supermassive black holes typically enter long quiet periods. They don't constantly feed. They wait for gas clouds or stars to wander too close. Unless something nudges material inward, the black hole remains inactive. Gravity alone doesn't drag in everything nearby. The idea of a black hole as a cosmic cleaning machine simply doesn't match observations. Another aspect that helps clarify this picture is the relationship between velocity and escape. For any object at any distance from a massive body, there is a certain speed required to escape its gravitational pull. At Earth's surface, that speed is around 11 kilometers per second. For the Sun, it's much higher. For the region near Sagittarius A, escape speeds vary depending on distance, but the key point is that objects don't randomly fall inward. They must lose velocity or be slowed down by something, otherwise they maintain their orbits. One might imagine that the event horizon acts like a magnet, pulling in everything that gets too close. But even right outside the event horizon, an object with enough sideways velocity can orbit without falling in. These orbits would be unstable extremely close to the black hole, but for distances slightly larger. Stable orbits exist. The edge where time slows doesn't function as a suction point. It's simply where escape becomes impossible. Outside that point, motion remains flexible. You can orbit. You can move outward. You can even escape entirely if your speed is high enough. That freedom disappears only when you cross the boundary where no outward path remains. The difference between a black hole and a vacuum cleaner lies in this fundamental idea. Vacuum cleaners create pressure differences that suck in air and debris. Black holes create no pressure differences. They simply curve space. Objects follow the curves. If the curve leads to an orbit, the object stays in orbit. If the curve leads inward only after losing energy, the object drifts slowly. If the object crosses the event horizon, the inward curve becomes inevitable. But outside that region, gravity behaves exactly as expected. Another common misconception involves the idea of black holes growing rapidly. While some black holes in distant galaxies grow quickly during active feeding phases, Sagittarius A grows extremely slowly today. The rate at which it gains mass is tiny. It would take billions of years to significantly increase its mass at the current rate. Most of the material near it remains in stable orbits, or interacts with gas in ways that don't result in large infalls. The black hole simply waits for long time scales for material to drift inward. Even when stars come close to a black hole, they usually aren't consumed whole. Most stars remain in stable orbits. Rarely a star passes so close that tidal forces pull it apart. This event, called a tidal disruption, creates a bright flare observable from far away. Such events are extremely rare for Sagittarius A. They happen perhaps once in tens of thousands of years. The chances of witnessing one in real time are incredibly small. The vast majority of stars near the core keep their distance comfortably. It's also important to understand that black holes don't move around looking for things to swallow. They remain where they are unless something with enough mass moves them. Sagittarius A isn't roaming through the galaxy. It sits at the centre because the overall gravitational field places it there. The stars orbit it, not because it is hunting them, but because they formed within or migrated into the gravitational environment that makes the centre the most stable position for a massive object. Motion in the galaxy isn't chaotic. It follows patterns shaped by mass distribution. Even hypothetical scenarios where a black hole drifts through space pulling objects inward misunderstand how gravity works. A wandering black hole wouldn't vacuum everything behind it. Its gravitational pull would attract objects only within a certain limited range. Anything outside that range wouldn't be affected, and even for objects inside that range, the pull wouldn't be irresistible unless their velocity relative to the black hole were low. Most stars move fast enough that a passing black hole would alter their motion slightly without capturing them. This stable, predictable behavior is reflected in the environment near the center of the Milky Way. Stars orbit, gas flows, occasionally matter drifts inward, flares occur. But most of the time, Sagittarius A remains quiet. It isn't a threat to the galaxy. It's part of the structure that helps the galaxy maintain its shape. This idea becomes clearer when you consider that every massive object in the universe shapes the motion of objects nearby. Planets orbit stars. Stars orbit the centers of galaxies. Galaxies orbit within clusters. Black holes are simply massive objects following the same rules. They don't create chaos. They don't distort space in unexpected ways outside their immediate vicinity. Their influence weakens with distance. The stronger effects occur only near the event horizon, because the curvature of space becomes extreme. Farther away, their gravity looks like any other gravity. Sagittarius A doesn't consume the Milky Way. It doesn't threaten distant stars, planets, or solar systems. It sits quietly at the core, shaping the inner region through its mass, not through suction or aggressive motion. Its behavior is defined by the laws of physics in the same consistent way that every other object's behavior is defined. Understanding this helps shift the idea of black holes away from mystery and fear towards something more grounded. A black hole is not a monster in the center of the galaxy. It is a natural outcome of mass collapsing under its own gravity. It obeys the same rules as everything else. Its presence is important, but not dangerous to regions far from the event horizon. The center of the Milky Way is an environment unlike any other part of the galaxy. It isn't empty, it isn't quiet, it isn't a barren stretch of space where only gravity acts in silence. Instead, it is a crowded, active, constantly shifting region filled with gas, dust, stars, radiation, magnetic fields, and the remnants of countless past events. All of these components form an ecosystem shaped partly by the massive bulge of stars around the core and partly by the presence of the supermassive black hole, which sits in the middle like a steady, unseen weight affecting everything without announcing itself. This ecosystem doesn't grow in the biological sense, but it evolves over millions of years as each part interacts with the others. When astronomers look into this region with infrared and radio telescopes, they see structures that don't resemble the orderly spirals in the outer disk. Instead, they see clumps, streams, rings, filaments, and arcs of material. These structures shift over long periods, but even in the short term they show activity. Gas clouds drift, dust lanes stretch, stars move so quickly that their positions can be tracked over human timescales. Everything is packed into a volume far smaller than the spaces between stars near where the sun resides. The density alone changes how the region behaves. One of the most noticeable features is the central molecular zone. This is a thick, dense ring of gas that occupies hundreds of light years around the center. It contains a significant portion of the galaxy's molecular hydrogen, the raw material needed for star formation. But star formation in this region doesn't follow the same predictable patterns found in calmer parts of the galaxy. The conditions near the core are more turbulent, the gas is hotter, and the motion is more chaotic. Shock waves travel through the material, compressing some regions and dispersing others. The gravitational influence of the bulge and the black hole ensures that gas doesn't settle into a simple disk. Instead, it forms a dynamic, constantly changing ring with dense pockets where new stars might eventually form. These pockets don't remain static. Some collapse under their own gravity and begin forming stars. Others are torn apart by tidal forces or disrupted by nearby radiation. Some drift inward over time, pulled gradually toward the center by interactions with magnetic fields or other gas streams. As they move, they heat up or cool down depending on their density and their proximity to energetic regions. The result is an environment that doesn't stay still long enough for a single pattern to dominate for millions of years. Within this environment, past activity from Sagittarius A plays a significant role. Although the black hole is quiet today, evidence suggests that it was more active in the past. Astronomers have found clues in the form of enormous bubbles of high-energy particles extending far above and below the galactic plane. These structures, discovered through gamma-ray observations, indicate that something powerful happened near the core millions of years ago. The bubbles likely formed when the black hole consumed a larger amount of gas, or when a burst of star formation near the center produced strong winds and shock waves. Whatever their origin, they show that the core has experienced periods of significant energy output. Even though the black hole doesn't produce constant activity, its long-term influence shapes the distribution of gas near the center. When gas falls towards Sagittarius A, it compresses and heats up. This heating changes the chemistry of the surrounding region. Molecules break apart or form in different ratios than those in calmer parts of the galaxy. Radiation from nearby massive stars also alters the gas. In some places, high-energy photons strip electrons from atoms, creating ionized regions where the gas glows in radio or infrared wavelengths. These glowing regions outline the edges of dense clouds, creating patterns shaped by both local and large-scale forces. The stars near the center add another layer to this ecosystem. Many of them are massive and young, burning their fuel quickly and shining intensely. Their light affects the gas around them. Their winds sweep through the region, pushing material aside, creating cavities, and triggering new waves of compression. When these massive stars reach the ends of their lives, they explode, adding more turbulence to the environment. The resulting shock waves move through the gas, heating it and altering its motion. These explosions also enrich the region with heavy elements, adding material that might eventually become part of future stars or planets. One challenge in understanding this ecosystem comes from the sheer number of influences at play. Gravity shapes the broad motions, but temperature, pressure, radiation, magnetism, and turbulence determine the finer structure. The black hole adds another layer, not by pulling everything inward, but by shaping the geometry of space in a way that influences how gas moves. Even when the black hole is quiet, its presence sets the gravitational baseline for the region. Gas clouds can't orbit too close without being stretched. They can't form stable disks unless their motion matches the gravitational pull. Over time, these conditions determine where stars form and where they don't. The central region also hosts unusual stellar populations. Some stars are very old, having formed billions of years ago when the galaxy was young. Others are surprisingly young, suggesting that star formation in the core hasn't stopped. The presence of young stars in such a harsh environment raises questions about how they formed. Some theories propose that gas clouds were compressed by shock waves from past activity, creating dense pockets that collapsed into stars. Another idea is that stars formed farther out and migrated inward through gravitational interactions. Whatever the case, these stars contribute to the ecosystem by emitting strong radiation, affecting gas flows, and enriching the region with heavy elements when they die. Even the orbits of these stars reveal impacts on the environment. Their motion stirs the gas, creating eddies and streams. Their gravity tugs on nearby material. Their collective mass contributes to the gravitational field that shapes the larger region. Over long periods, these effects accumulate, adding subtle changes to the overall structure. While the black hole is the most massive single object, the combined mass of the surrounding stars and gas outweighs it significantly. This mixture of influences helps create a dynamic balance within the core. Another important feature is the presence of magnetic fields. These fields thread through the gas in the central region, shaping its motion. Magnetic fields can twist and stretch gas clouds, preventing them from collapsing or helping funnel them inward. They influence how the gas heats up and cools down. They also affect how charged particles move, steering them into arcs or filaments. In some parts of the central molecular zone, these magnetic fields align into structures that are visible in radio wavelengths. These filaments sometimes stretch for dozens of light years. Their shapes reflect the combined forces of gravity, turbulence, and magnetic tension. Radiation also plays a major role. The central region emits light across the electromagnetic spectrum. Infrared light reveals warm dust. Radio waves highlight ionized gas. X-rays show areas where particles heat up through collisions. Together, these different wavelengths paint a detailed picture of an ecosystem that never rests. The radiation also affects the environment. In some places, it heats gas enough to prevent star formation. In others, it strips electrons from atoms, changing the chemical composition of the region. Over long timescales, radiation contributes to the cycle of heating and cooling that shapes the structure of the core. Every component of the central ecosystem interacts with every other component. Gas clouds collide, magnetic fields twist, stars orbit, radiation heats, shock waves compress. The black hole exerts gravitational influence. All of these factors together determine whether gas forms stars, drifts inward, or disperses outward. The region near Sagittarius A is not governed by a single process. It's shaped by the combination of many processes happening simultaneously. The presence of the black hole doesn't dominate the ecosystem, but it helps define its boundaries. Near the event horizon, the environment becomes extreme, but even outside that region, the gravitational pull influences how gas flows. Some gas spirals inward, forming a loose accretion flow. other gas orbits in stable paths farther out. Occasionally, gas clouds pass close enough to be stretched or accelerated. The heating from these interactions produces the flares observed in infrared or X-ray wavelengths. These flares don't change the overall structure of the ecosystem, but they provide moments of energy that ripple outward and influence the environment temporarily. One interesting aspect of this ecosystem is how star formation interacts with the black hole. When stars form, they often come in clusters. These clusters can migrate inward over time. If they get too close to the black hole, the tidal forces may disrupt them, scattering stars into different orbits. In some cases, individual stars may get flung outward at extremely high speeds, becoming hypervelocity stars that travel through the galaxy. These ejections are rare, but they illustrate how the black hole interacts indirectly with the environment. It doesn't reach out and grab stars, but it can influence their motion when they pass too close. Meanwhile, the gas that doesn't collapse into stars continues to orbit in complex patterns. Some of it moves outward due to pressure or turbulence. Some falls inward. The balance between these motions determines how much material reaches the black hole over time. Currently, Sagittarius A receives very little material. The gas flow is light. The region is relatively quiet compared to more active galaxies, but the potential exists for future changes. If a large gas cloud drifts inward, the black hole could become more active for a period. Such an event would change the radiation output and alter the surrounding ecosystem temporarily. Over long periods, the actions of the ecosystem leave signatures that astronomers can study. Shock waves from past events create arcs and shells in the gas. Heavy elements from dying stars enrich the central region. Radiation from the black hole during active periods leaves traces in the surrounding gas. The large bubbles above and below the galactic plane preserve evidence of significant energy output millions of years ago. Together, these signatures reveal the long-term story of how the core has evolved. Understanding this ecosystem is challenging because it requires piecing together information from many different wavelengths of light. No single telescope can see everything. Infrared telescopes reveal the stars. Radio telescopes show the gas. X-ray observatories highlight the high-energy events. Only by combining all these observations can astronomers build a complete picture of the environment around Sagittarius A. One of the surprising outcomes of these combined observations is the realization that the galactic center is far more structured than it appears in visible images. In visible light, the core looks like a hazy region obscured by dust. But when you remove the barrier by looking in infrared or radio wavelengths, the details emerge. Filaments stretch across the region. Gas rings curve into arcs. Dense clusters of stars glow brightly. Cavities carved by stellar winds dot the landscape. Everywhere, the signs of ongoing motion appear. Even the distribution of dust contributes to the ecosystem. Dust absorbs and re-emits light, influencing the temperature of gas around it. In some places, dust becomes so dense that it forms dark lanes. In others, it heats up and glows in infrared wavelengths. Dust grains also affect chemistry by providing surfaces for molecules to form. These molecules help cool gas, making star formation possible. Without dust, the ecosystem would behave very differently. All these components exist in a delicate balance. If the region were too hot, gas would disperse and star formation would slow. If it were too cold, gas would collapse too quickly, leading to bursts of star formation that could disrupt the environment. If the black hole were much more active, radiation could strip gas from the region or heat it enough to prevent collapse. If the black hole were absent, the gravitational field would be different, affecting the stability of the central structure. The current state represents a balance shaped by billions of years of evolution. Even though the black hole is quiet today, its steady gravitational influence continues shaping the inner few light years. Stars orbit in predictable paths. Gas flows around the center. Magnetic fields twist along curved lines set by the movement of material. Everything in the environment responds to the underlying gravitational structure. The black hole may not consume much, but its weight defines the central region's shape. As you move outward from the black hole, the environment gradually transitions from the extreme inner zone to the broader bulge. The bulge contains older stars with slower motion. Their combined mass adds to the gravitational field, influencing how the gas in the central molecular zone orbits. The bulge merges into the bar structure, which channels gas inward from the spiral arms. This inflow of material ensures that the central ecosystem doesn't run out of gas. Even though star formation and occasional infall remove material from the region, gas continues to arrive over long timescales, maintaining the cycle. The spiral arms farther out also influence the central region. They act like conveyor belts, moving gas inward slowly. Over millions of years, this gas makes its way toward the core, contributing to new star formation and occasionally feeding the black hole. The entire galaxy is connected through these motions, and the centre acts as the reference point around which everything revolves. This overall motion, spanning tens of thousands of light years, forms the larger galactic ecosystem. The hidden heartbeat at the core, quiet but influential, helps set the structure of the galaxy. It doesn't dominate the system through force, it shapes it through mass. That mass curves space, and that curvature guides motion. Over time, the motions settle into stable patterns. These patterns become the long-term structure of the Milky Way. Studying the centre of our own galaxy doesn't just reveal what happens in the Milky Way. It provides a reference point for understanding something that appears to be a universal pattern across the cosmos. Nearly every large galaxy astronomers have examined shows evidence of a massive object in its core, often millions or billions of times more massive than the Sun. These objects behave in ways that resemble Sagittarius A, even though the environments around them vary widely. Because Sagittarius A is close enough for scientists to measure its effects directly, it becomes a model that helps interpret what is happening in galaxies far beyond our reach. Galaxies come in many shapes. Some form tight spirals, others are more irregular. Some form giant ellipses that contain hundreds of billions of stars without the structured arms seen in spiral galaxies. But across all these forms, the centres follow similar rules. The presence of a supermassive black hole changes how matter moves in the inner regions, sets the stability of the core, and influences how gas flows over long timescales. By studying Sagittarius A in detail, astronomers can apply the same principles to galaxies where direct measurements are almost impossible. One of the clearest lessons comes from understanding how stars orbit near a massive object. In the Milky Way, the fast-moving stars near the centre reveal exactly how strong the gravitational pull is and confirm that the mass must be concentrated in a small region. When astronomers see stars in other galaxies moving quickly around their cores, they can infer that something similar must be present. But because these galaxies are far away, individual stars cannot be tracked in the same detail. The motion appears blended together. Instead of individual paths, astronomers see the combined effect of many stars moving in different directions. The result is a broad measurement of velocity dispersion, essentially a measure of how fast stars are moving in all directions. Sagittarius A sets the expectation for how mass and stellar motion relate. It offers a clear example of how fast stars should move near a particular amount of mass. Scientists can then use this information to estimate the mass of black holes in distant galaxies. They can compare the expected speeds to what they observe. The closer the match, the more confident they become that supermassive black holes are a normal part of galactic evolution. Another lesson comes from understanding how galaxies feed their central black holes. Sagittarius A is quiet now, but the evidence of past activity shows that central black holes can transition between active and inactive phases. In some galaxies, these phases produce intense light, jets of plasma or winds strong enough to push gas outward. These active galactic nuclei shine so brightly that they can be seen across billions of light years. But the underlying physics is the same as the quiet periods. Gas flows inward gradually, heats up, and emits energy. Sagittarius A demonstrates the quieter end of this process. Other galaxies show the louder end. Together they form a full picture of how black holes grow over time. Because Sagittarius A currently consumes so little matter, it offers a chance to study a black hole in a resting state. Many distant galaxies contain black holes that are actively feeding, which makes it difficult to study their gravitational effects without interference from the light produced by infalling gas. Sagittarius A doesn't have this issue. It lets scientists measure the structure of the central region without overwhelming brightness. This quiet behavior reveals the natural dynamics of stars and gas near a supermassive black hole, when feeding isn't dominating the environment. This helps astronomers interpret quiet galactic centers elsewhere. When a distant galaxy shows a calm core with no bright emissions, it doesn't mean the black hole is absent. It may simply mean the black hole is in the same resting phase as Sagittarius A. Understanding the quiet times is just as important as understanding the active times, and our central black hole provides the clearest example of what a quiet, supermassive black hole looks like. Comparisons also extend to the relationship between the mass of a galaxy and the mass of its central black hole. Observations across many galaxies show that these two masses correlate closely. Larger galaxies tend to have larger black holes. This correlation suggests that the evolution of a galaxy and the growth of its black hole are linked in some way. Sagittarius A fits perfectly on this curve. Its mass of about 4 million suns matches what would be expected for a galaxy the size of the Milky Way. This fit provides confidence that the relationship is real and not just a coincidence. The correlation doesn't imply that the black hole controls the galaxy. Instead, both may form through related processes. When galaxies form and merge, gas flows inward. Some of that gas forms stars. Some feeds the black hole. Over billions of years, these processes balance out in a way that creates a consistent ratio. Because Sagittarius A matches the expected value, it reinforces the idea that this ratio holds across different environments. Another important insight involves the structure of the gas near the center. In many galaxies, gas clouds orbit the black hole in rings, disks, or spirals. Some of these structures resemble the central molecular zone in the Milky Way. By studying the detailed motion of gas near Sagittarius A, astronomers can model how similar structures behave in other galaxies. They can apply these models to systems where direct observation is limited by distance or resolution. This comparison helps them estimate gas density, temperatures, star formation rates, and the likelihood of feeding events. When observing distant galaxies, scientists also rely on the behavior of light near the event horizon to identify black holes. The image of Sagittarius A from the Event Horizon Telescope shows the characteristic shadow expected for a black hole of a particular mass. That shadow shape matches theoretical models of rotating black holes. When astronomers observe galaxies with bright cores but cannot resolve the shadow, they still recognize the signature of a black hole by comparing the brightness patterns and shapes to models tested against Sagittarius A and the black hole in M87. The existence of a local example helps ensure that these models reflect real physics, not just theoretical predictions. By analysing how Sagittarius A interacts with its environment, astronomers also gain insight into how black holes affect their host galaxies on long timescales. Even though Sagittarius A is quiet today, its past activity left traces in the form of large-scale bubbles above and below the galactic plane. These structures show how energy released by a black hole can influence gas far beyond the core. In distant galaxies, similar bubbles appear, sometimes even larger, and the energy output is often greater. Sagittarius A offers a smaller-scale version of the same phenomenon. Studying it helps astronomers understand how energy from the core shapes the galactic halo, changes the temperature of gas, and influences star formation far from the centre. The Milky Way also shows how black holes interact with galactic bars. The Milky Way contains a bar structure that stretches across the central region, channeling gas inward. In simulations of galaxy evolution, bars often drive gas toward the central black hole, triggering periods of increased activity. Sagittarius A's quiet state indicates that while the bar does supply gas, the flow isn't always fast enough to create strong feeding events. Understanding this balance helps astronomers interpret whether bars in other galaxies are fueling their central black holes, or simply moving gas around without triggering active phases. Studying Sagittarius A also helps refine theories about how black holes form. The presence of a supermassive black hole in the Milky Way's centre suggests that such objects formed early in the galaxy's history. Distant galaxies observed in early cosmic epochs already contain massive black holes, some even larger than Sagittarius A. This raises questions about how these objects formed so quickly. Sagittarius A may represent the quieter descendant of an early black hole seed that grew modestly over time. Comparing it to more active distant black holes allows scientists to consider different growth pathways. Some black holes grow rapidly during early stages, while others grow slowly over billions of years. Sagittarius A fits into the slow growth category, offering a counterpoint to rapid growth models. The motion of stars in the core also reveals something about the early stages of galaxy formation. The mixture of old and young stars near Sagittarius A shows that star formation has occurred in the central region at different times. By examining the ages and compositions of these stars, astronomers can compare the Milky Way's central history to other galaxies. Some galaxies show only old stars in their cores, while others show evidence of recent formation. Sagittarius A provides a template for how star formation can continue even in harsh environments. This helps explain why some distant galaxies still produce stars near their cores, while others do not. The presence of young stars in the Milky Way's centre also answers questions about the role black holes play in star formation. For a long time, scientists wondered whether black holes suppress star formation by heating gas too much for it to collapse. Sagittarius A suggests that while black holes can influence star formation, they don't necessarily stop it. Under the right conditions, even the region near a supermassive black hole can produce new stars. This lesson helps clarify why some galaxies have star-forming cores, while others do not. Studying Sagittarius A also informs the search for intermediate mass black holes, which are thought to exist between the size of stellar black holes and supermassive ones. By understanding how mass accumulates at the centre of a galaxy, astronomers can look for signs of smaller black holes merging or interacting within the core. Some galaxies show evidence of multiple black holes in their early stages. Sagittarius A, with its stable environment, offers a contrast. If the Milky Way once had multiple black holes in the centre, they likely merged long ago. Learning how this merger process works helps explain how supermassive black holes reach their enormous sizes. The structure of the Milky Way's central region also provides insight into galaxy mergers. When galaxies collide, their central black holes eventually sink toward the middle of the merged system. Studying Sagittarius A shows how a black hole settles into the core and how the surrounding matter rearranges itself afterward. Other galaxies show signs of recent mergers, with dual black holes or irregular central structures. Sagittarius A represents the end stage of this process, providing a stable example of what a settled galaxy centre looks like. Comparing it to merging systems helps astronomers trace the evolution of galaxies over long timescales. Even the quiet behaviour of Sagittarius A contributes to our understanding of active galaxies. Because the Milky Way's black hole is in a resting phase, scientists can study how the environment looks when the black hole isn't overwhelming the core with radiation. This baseline helps them separate the effects of feeding from the effects of normal stellar activity. When they observe distant galaxies with active cores, they can subtract the baseline processes observed near Sagittarius A to isolate the influence of the black hole itself. Another important insight comes from the alignment of the black hole's spin. The shape of the shadow observed by the Event Horizon Telescope, along with the motion of the surrounding gas, provides clues about how fast Sagittarius A rotates. The spin affects how space curves near the event horizon. In other galaxies, black hole spin may influence the direction of jets or the distribution of energy. By measuring Sagittarius A's rotation, astronomers can refine models for how spin evolves through feeding events or mergers. These models help explain why some galaxies produce powerful jets, while others remain quiet. Sagittarius A also helps clarify how black holes interact with dark matter. Although dark matter dominates the mass of galaxies, it doesn't interact with light and is difficult to study directly. By understanding the gravitational environment near the center of the Milky Way, scientists can estimate how much dark matter exists in the core and how it might affect the motion of stars. Comparing this with other galaxies allows astronomers to test whether dark matter behaves similarly across different environments. Sagittarius A provides the closest and clearest opportunity to study this interaction. All these lessons combined show that the center of the Milky Way is not just a local curiosity. It is a key part of understanding how galaxies form, evolve and behave across the universe. Sagittarius A provides an anchor point for theories, a reference model for comparisons, and a detailed example of processes that occur too far away to observe directly elsewhere. The calmness of the Milky Way's center allows for measurements that would be impossible in more active environments, while the traces of past activity reveal how black holes influence galaxies during brighter phases. Looking ahead into the evolution of the Milky Way means thinking on timescales that stretch far beyond anything we experience in daily life. Stars move through their orbits over hundreds of millions of years. Gas drifts inward or outward over similar spans. Entire patterns shift slowly as gravity continues shaping the galaxy. Sagittarius A remains at the center of all this motion, not as an active force trying to guide the future, but simply as the heaviest object in the region, providing a gravitational anchor that everything else responds to. Its influence is steady and predictable, helping define how the galaxy will change over long periods of time. Right now, the Milky Way is in a relatively stable phase. The spiral arms are well formed, the bar structure channels gas toward the central region. The outer disk rotates in a pattern that hasn't shifted dramatically for billions of years. Even the central region, though crowded and complex, behaves within a familiar range. The black hole is quiet, consuming very little gas. The stars near the center orbit quickly but predictably. Gas clouds collide or drift, but no large-scale disturbances dominate the environment. The conditions aren't static, but they follow established trends. As time moves forward, these trends will continue shaping the galaxy. Stars in the central region will complete countless orbits around Sagittarius A. Their motion will gradually alter the environment as they interact with gas and dust. Some stars will exhaust their fuel and end their lives as white dwarfs, neutron stars or black holes. Others will explode in supernovae, injecting energy into the surrounding region. These local changes won't alter the overall structure of the galaxy immediately, but they will contribute to the long-term evolution of the central ecosystem. In the broader disk, new stars will continue to form from collapsing gas clouds. This process will eventually slow as gas reserves diminish. Star formation depends on the availability of cool, dense clouds. Over billions of years, as gas becomes more dispersed and heated, fewer regions will have the right conditions to collapse. The galaxy will gradually transition from a younger, star-forming environment into an older, quieter one. This transformation is common in spiral galaxies. Many galaxies observed today show reduced star formation compared to earlier cosmic periods. The Milky Way is expected to follow a similar path. Sagittarius A will continue influencing the trajectory of gas and stars near the center. It won't drive the evolution of the entire galaxy on its own, but it will remain a crucial component of the gravitational structure. Over long timescales, some gas from the central molecular zone will drift inward. Most of it will orbit for millions of years before losing enough energy to draw closer. If a particularly large gas cloud approaches the black hole, it could create a period of increased activity. During such events, the black hole would heat the infalling gas, producing stronger radiation and possibly shaping the surrounding region temporarily. These active periods would be brief compared to the age of the galaxy, but they would leave marks on the environment, just as past activity left large bubbles rising above and below the galactic plane. The central region may also experience changes as stars migrate inward through interactions with other stars or clusters. Over long periods, gravitational interactions slowly rearrange the distribution of stars. Heavy stars and remnants tend to sink toward the centre, while lighter stars drift outward. This slow process, called mass segregation, creates a more concentrated core over time. Sagittarius A will continue residing at the very centre of this distribution. As more stellar remnants accumulate nearby, the environment may become even more crowded with compact objects such as neutron stars and small black holes. These compact remnants won't necessarily fall into Sagittarius A, but they will interact with one another. In rare cases, collisions or mergers might occur near the core, releasing bursts of energy. The orbits of stars near Sagittarius A will also evolve subtly. Relativistic effects influence their motion, causing gradual shifts in their trajectories. Over millions of years, their orbital paths may precess, change shape, or exchange energy during close encounters with other stars. These changes are tiny on short timescales but significant over vast spans. The overall distribution of stellar orbits may gradually smooth out as random interactions redistribute energy. Farther out, the structure of the spiral arms will slowly adjust. Spiral arms are not permanent structures. They are density waves that move through the disk as stars orbit. Over long timescales, the arms may shift, tighten, or change shape. The bar in the central region may lengthen or shorten. It may rotate at a different speed, or evolve as stars migrate inward or outward. These changes affect how gas flows into the central region and, by extension, how often the black hole might receive new material. Eventually, one of the largest shifts in the Milky Way's future will come from an event far outside the galaxy itself. The Andromeda Galaxy, our nearest large neighbour, is moving toward the Milky Way. In a few billion years, the two galaxies will begin to merge. This process will unfold over a long time, perhaps a few billion years from the first encounter to the final settling of the merged system. During this time, the gravitational fields of both galaxies will distort one another, stretching their shapes and triggering waves of star formation as gas clouds collide. The black holes at the centres of each galaxy will gradually move toward the centre of the new combined galaxy. The presence of Sagittarius A during this future merger offers insight into what will happen. It will not be thrown out of the galaxy or swallowed instantly by Andromeda's black hole. Instead, both black holes will sink toward the centre of the merged system through interactions with stars and gas. Eventually, they will orbit one another, losing energy through gravitational waves until they merge into a single, larger black hole. This final merger will release a burst of gravitational energy that ripples through space. But the process will be quiet in terms of visible light unless large amounts of gas fall toward the merged black hole during or after the event. During the merger of the galaxies, the structure of the Milky Way will change dramatically. The spiral arms will distort and eventually fade. The combined system will likely form an elliptical galaxy, with stars distributed in a more uniform, rounded shape rather than a flattened disk. Star formation will spike for a time due to gas collisions, then gradually decline as the gas is consumed or heated. Sagittarius A's successor, the merged central black hole, will reside at the heart of this new galaxy, continuing to influence the motion of stars near the core just as Sagittarius A does today. Looking even farther into the future, after the merger and the eventual slowdown of star formation, the galaxy will continue aging. Stars will exhaust their fuel. Many will fade into white dwarfs, cooling slowly over trillions of years. Some will collapse into neutron stars or small black holes. The remaining gas will become sparse. Without new stars forming frequently, the galaxy will grow dimmer. Sagittarius A's descendant will still be there, but the environment around it will be quieter. The inflow of gas will slow even more. Feeding events will become rare. The black hole will grow slowly, accumulating only small amounts of mass from the occasional star or gas cloud that drifts too close. Even then, the black hole will remain important. It will continue anchoring the central gravitational structure of the system. Stars that continue to orbit the core will follow predictable orbits shaped by the combined mass of stellar remnants and the black hole. Over incredibly long timescales, interactions among stars and black holes near the core may eject some objects outward. Others may drift closer. Even in these distant eras, gravity's steady pull remains the guiding force. At even grander timescales, long after galaxies have aged and star formation has ceased, the universe itself may shift into phases where matter becomes more diffuse. Some theories suggest that over trillions or quadrillions of years, stars will disperse, galaxies will drift apart due to cosmic expansion, and remaining matter may fall into black holes. If such a phase occurs, Sagittarius A's descendant will become one of the long-lived objects in the universe. Black holes evaporate extremely slowly through a process called Hawking radiation. But for supermassive black holes, this process takes far longer than the current age of the universe. The eventual evaporation of Sagittarius A's descendant would occur over timescales so long that they are difficult to describe meaningfully. While this future is extremely distant, the near-future evolution of the Milky Way is easier to understand. Over the next few billion years, the structure of the galaxy will remain mostly stable. Spiral arms will continue rotating. The bar will continue channeling gas toward the center. Star formation will gradually decrease as gas is used up. Sagittarius A will remain quiet most of the time, occasionally flaring as small pockets of gas fall inward. Stars near the center will continue orbiting rapidly. The central molecular zone will continue to shift, producing new stars sporadically. The overall appearance of the galaxy will not change dramatically on human timescales. The long-term future of the Milky Way is not something driven by sudden events. It unfolds gradually as gravity moves matter through the galaxy. Sagittarius A plays a steady role in this evolution. It doesn't dictate the future. It contributes to the gravitational structure that guides the future. That contribution will continue for as long as the galaxy exists in its current form. By studying Sagittarius A and the trends visible today, astronomers can forecast these long arcs of change. They understand how gas flows through the bar. They understand how spiral arms evolve. They recognize how mergers reshape galaxies. They see how quiet black holes and active ones differ. These insights allow for predictions that span billions of years. While no one can say precisely what the Milky Way will look like at every stage, the general patterns are clear. The story of Sagittarius A stretches from the smallest scales where space curves into steep gradients to the broader shape of the entire Milky Way, where stars, gas and dark matter move in slow coordinated patterns around a center they will never reach. Even though the black hole itself remains hidden behind dust and the limit of its own gravity, its presence shapes what the galaxy has become. Looking back across the path taken through these ideas, everything connects in a way that brings the distant and the immediate into a single view. The center of the galaxy may seem remote, unreachable, and almost unreal, but its influence is part of the same structure that includes the Sun, Earth, and every star visible in the night sky. Thinking about this connection doesn't require focusing on the extremes or the complicated mathematics of space-time. It comes down to understanding that our position in the galaxy isn't separate from the events happening near the core. Even though Sagittarius A is far away, its mass contributes to the shape of the galaxy that holds us. The curve of the spiral arms, the rotation of the disk, and the structure of the bar all relate indirectly to the presence of the central mass. Everything in the Milky Way participates in the same, larger pattern. That pattern unfolds slowly, but it includes every part of the galaxy, from the crowded core to the quiet outskirts where our solar system orbits. When you look up at the night sky from Earth, it's easy to feel that the stars have little to do with the center of the galaxy. The sky looks calm, the stars appear fixed. The Milky Way, when seen from a dark location, stretches like a soft band across the sky. But all those stars are part of a structure that rotates around Sagittarius A. Every star you see carries momentum shaped by the gravitational pull of the galaxy's mass, including the central black hole. The spiral arms aren't static, they aren't painted onto the sky. They're density waves created from the collective motion of stars and gas responding to the gravitational field of the whole system. The center sets the balance. It doesn't control everything, but without it, the galaxy would not look the way it does. This broader view helps put the details of the central region into context. The fast-moving stars near the core, the dense molecular gas, the magnetic filaments, the glowing arcs, the quiet black hole, and the echoes of past activity all represent the most intense expression of the Milky Way's dynamics. But those dynamics extend outward across tens of thousands of light years. They influence regions where stars form calmly in the outer disk. They influence streams of gas that move along the arms. They influence how star clusters orbit the center and how the disk maintains its thickness. Even the slow drift of the Sun along its galactic orbit traces back to the same gravitational foundation. It's not often that a single object provides insight into so many aspects of a system. Sagittarius A does so because it sits at the deepest part of the gravitational well. When scientists measure how stars move near the center, they gain information about how gravity behaves at its most intense. When they look at gas flowing through the bar and into the core, they learn how galaxies redistribute their material. When they observe the quietness of the black hole today, they understand the difference between active and inactive phases. When they identify signs of past activity, they see how central engines can shape the larger halo. When they compare Sagittarius A to black holes in other galaxies, they see where the Milky Way fits in the broader universe. All of these threads form a picture that's more complete than what was possible even a few decades ago. Telescopes that see in infrared, radio, and X-ray wavelengths revealed layers of structure that were invisible before. Precise measurements of stellar motion tracked years of change that gradually mapped the core. Flares near the event horizon provided brief moments of rapid activity. The Event Horizon Telescope offered a direct look at the shadow of the black hole. Each observation contributed another piece to the puzzle. Even though the black hole cannot be seen directly, the accumulation of evidence leaves no doubt about its presence or its role. The way these discoveries unfolded also highlights something about how knowledge grows. None of the observations alone would have been enough to explain the center fully. It was the combination of clues from across the spectrum that revealed the structure. Radio waves passing through dust showed the first signs of a compact source. Infrared images exposed the fast-moving stars. X-ray signals pointed to gas heating near the core. Each data set confirmed aspects of the others. Together they built a consistent explanation. This layered approach is part of why the understanding feels solid. It doesn't rely on a single measurement or assumption. It rests on decades of independent yet connected observations. Reflecting on all of this also brings attention to the scale involved. Sagittarius A is enormous by human standards, but moderate by cosmic ones. Its mass is measured in millions of suns, yet it sits in a galaxy weighing hundreds of billions of solar masses. The Milky Way itself is only one galaxy among trillions, and yet, when studying just this one black hole, scientists have gained insights that apply across the universe. The behavior of gravity near Sagittarius A helps refine models that describe gravity everywhere. The motion of stars around it reveals how mass shapes space across all scales. The relationship between the black hole and the galaxy helps clarify how galaxies evolve over billions of years. This connection between local study and universal application is part of what makes the story compelling. It shows that understanding something distant can improve understanding of everything closer. It shows that local details can reveal global patterns. It shows that the structure at the center of one galaxy can reflect the structure at the center of many others. Sagittarius A becomes a representative example, not because it is unique, but because it is accessible enough to measure accurately. Thinking about the accessibility also highlights the role of technology. Instruments capable of seeing through dust made it possible to observe the center at all. Interferometry allowed scientists to measure positions and motions with accuracy that would have seemed impossible earlier. Space-based observatories extended the range of wavelengths that could be studied. Data processing techniques improved until mountains of observations could be combined into meaningful images and patterns. None of this makes the center any closer, but it makes it more visible. Even though humans will never travel physically to the region near Sagittarius A, the tools now exist to learn about it with remarkable clarity. These insights don't just extend outward into the cosmos, they also extend inward to a human perspective. Thinking about the center of the galaxy can shift how the familiar sky looks. The stars you might see on any clear night don't appear connected to the black hole, but they orbit within the same gravitational field. Their motion, though too slow to see by eye, reflects the same forces studied near the core. The quietness of the night sky, the patterns of constellations, and the calmness of Earth's place within the galaxy all exist within the structure shaped partly by Sagittarius A. The distance makes the influence hard to sense, but the connection is real. This sense of connection can also make the galaxy feel more unified. It isn't just a collection of unrelated stars scattered across space. It's a structure shaped by mass, motion, and time. The black hole at the center, the stars in the arms, the gas drifting through the spiral pattern, and the dark matter holding everything together all belong to the same system. Even if most of the galaxy remains out of reach, the physical laws linking each part allow for a complete understanding. Observing the night sky from Earth also offers a way to appreciate the scale of time involved. Everything described in the galaxy evolves slowly. Stars take millions or billions of years to complete orbits. Gas moves gradually along the arms. The black hole grows tiny fractions of mass compared to its size. Nothing in the galaxy changes quickly from a human standpoint. This slow pace can offer a sense of steadiness. The patterns that shape the Milky Way are stable enough to last far longer than human civilizations, human histories, or even human lifetimes. Understanding these timescales doesn't diminish the significance of daily life. It provides perspective on how small disturbances or rapid changes fit into a larger stable structure. There's also something grounding about knowing that much of the galaxy remains predictable. Even though the center can produce occasional flares or brief periods of activity, the long-term structure is steady. Stars continue orbiting. Gas follows familiar paths. Gravity continues shaping motion. The core remains dense and quiet most of the time. The future of the Milky Way will unfold slowly. Even the coming merger with Andromeda will play out across billions of years, not in sudden catastrophic moments. The black hole will continue acting as a stable part of the system throughout those changes, adapting as the galaxy evolves around it. This gradual nature of galactic change stands in contrast to how quickly aspects of human life can shift. It can feel reassuring to look at something measured not in days or years, but in millions or billions of years. The galaxy doesn't rush. It doesn't demand immediate responses. Its changes unfold at a pace that allows for reflection. Understanding the motion and structure of the Milky Way provides a wider frame that can make everyday concerns feel smaller without minimizing their importance. It shows that the universe allows space for both short-lived events and long-term patterns. As the view pulls back from the technical details, the core of the story remains straightforward. Sagittarius A sits quietly in the heart of the galaxy. It doesn't draw attention to itself. It doesn't shine. It simply exists as a concentration of mass shaping the motion around it. The stars respond to that mass. The gas responds to it. The spiral pattern responds to it. Over time, the galaxy continues evolving around this central weight, adjusting slowly as new events unfold and old patterns shift. Understanding this story doesn't require traveling across the galaxy. It comes from observing the sky, building tools that extend perception, and studying the behavior of light and motion. Every data set, every refined measurement, and every improvement in technology adds clarity. That clarity allows scientists to describe the environment around Sagittarius A with confidence and detail, even though no one will ever see the center with their own eyes. Standing somewhere beneath the spiral arms, whether in a quiet place at night or in a room where the sky remains out of view, it's possible to imagine the galaxy as a connected whole. The stars overhead form only a small fraction of what exists. The core lies far across the sky, hidden behind dust but understood through patient effort. Everything rests within the same structure. Each orbit, each stream of gas, each cluster, and each region of dust share the same larger environment. This understanding doesn't require exaggeration or dramatic interpretation. It simply shows that the Milky Way is a stable, evolving system shaped by the combined weight of stars, gas, dark matter, and the black hole at its center. The motions respond to gravity. The patterns persist over long periods, and the core remains part of the structure, influencing but not dominating the whole. As the exploration ends, the view returns to the present moment. Nothing in the galaxy has changed while the ideas have unfolded. The stars continue moving at their slow pace. The black hole remains quiet. The spiral arms hold their shape. The Milky Way continues rotating, and all of it remains connected by the same gravity that extends from the core out to the edges of the disk. Understanding that connection brings the distant into the same frame as the nearby, tying the vast structure of the galaxy to the point where you are now, beneath the same spiral arms that have turned for billions of years and will continue turning long after.